Welcome to the series on understanding Java performance. Throughout this series, we're going to learn about the types of things HotSpot does to make your code run faster. Unlike a lot of performance series, rather than focusing on changes you can make, we're going to talk about what HotSpot already does for you and how you can help it out. To do that, we're going to have to learn about a lot of the components of HotSpot. We're going to have to learn about the HotSpot lifecycle, how the interpreter works with the VM to gather profiling data, which feeds into the just-in-time compiler, which through the magic of de-optimization and having a way to correct its mistakes is allowed to do speculative optimizations, which allow us to write Java code that can actually run faster than similar C or C++ code. We're also going to learn about the class file format and what a class file looks like, and about the Java bytecode. But mostly we're going to focus our attention on the types of optimizations the just-in-time compiler performs. We're going to talk about intrinsic methods and static optimizations, both local and global, and interprocedural optimization, and speculative optimizations, and all the various tricks that VM has to make dynamic calls run fast. But also about the consequences, de-optimization, which lets us do cool optimizations, but does come with a latency penalty. In fact, de-optimization occasionally stops the world. And more importantly, you're going to learn why these optimizations matter and how they all fit together, and the surprising things that you can do that get in the way of them working. Things that you would think should optimize your code can actually backfire. And these optimizations come with some surprising implications when we're trying to write concurrent code. To help us see all these things, we're going to introduce a lot of tools. Jitwatch to see what the just-in-time compiler is doing, all the way down to the machine code. Java measurement harness to benchmark our application's performance, and mission control to accurately profile our application's behavior. Many profilers today can lie to you, but you may not know it. And most importantly, through all of this, I want you to learn how to write code that HotSpot can optimize for you. This will allow you to avoid a lot of unnecessary work. Many types of optimizations I see people doing, they just don't need to do because the compiler already knows how to do them. And you'll learn a few simple tricks that can help the compiler so it can do even more work for you. That way your code can run fast without you having to do too much at all. Next time, we'll get started by looking at the anatomy of a compiler. To start our exploration to Java performance, we're going to look at the parts that make up a compiler. Our goal is to answer, how does code execute? How do we get from the Java code that you or I write to actually running on the hardware? As it turns out, every compiler, no matter what language it's for, goes through the same basic steps. The first step is parsing. We take the source language, in our case Java, and we turn it into a form that's easier for the compiler to work with. Once it's in that form, the compiler may perform some optimization before running it so that our code will run faster, and then finally, of course, we'll execute the code. Parsing itself is actually comprised of several substeps. First step is to take the Java code and through a process called lexical analysis to turn it into what are called tokens. And then the actual parsing phase is to turn those tokens into what's called an abstract syntax tree, or what compiler people would call an AST. That may all sound a bit abstract, but you've probably actually done this even if you've never taken a compiler course. Essentially, parsing is just sentence diagramming. So if we take the statement foo equals 30 plus 2, the tokens are the words I just said, foo equals 30 plus and 2. And then we diagram the statement, rooting our trees at operators. So in this case, equals and plus. So our tree is rooted at equals, with foo as the left-hand side, and a right-hand side, which is a subtree of the sum of 30 and 2. Pretty straightforward. Now, you may have heard people go on and on about how beautiful Lisp is, and honestly, they're right. If you look at this S expression, let foo be 30 plus 2, it's just a direct representation in a textual form of the abstract syntax tree. Let is equals. That's the root of our tree. The first operand to let is foo. That's our left-hand side. And then we have this sublist, which is the sum of 30 and 2, and that's our subtree of plus 30 and 2. So every other language, we go through all this heavy machinery to turn our human readable form into this abstract syntax tree. In Lisp, we're just sort of working with the abstract syntax tree directly, And there is something elegant about that. Now, if you took a compiler class in college, you probably almost exclusively spent your time talking about parsing. But frankly, for most compiler writers, the parsing is the boring part. The parsing is actually what we call the front end of the compiler. Now, that may seem like a strange term, but you have to understand that for a compiler, you are the end users. Your interface to the compiler is writing Java code, and so that is the front end of the compiler. But the more interesting work, the part that actually affects performance, goes on in what is called the back end, where the optimization occurs and where the execution occurs. And we actually separate the compiler into a front end and a back end. And by separating the compiler into a front end and a back end, we can actually do something rather cool. You might have wondered, how many compilers do we have to write? If we wanted to make a C compiler for x86, and a C compiler for Spark, and a C compiler for ARM, do we have to write 3 different compilers? And then do we have to write 3 more compilers for Fortran, and 3 more compilers for C++? The answer is no. If you look at something like the GNU compiler collection, what it does is it introduces what's called an intermediate representation. So this is a representation somewhat like the AST, but that's language agnostic. So we have a front end from C to the intermediate representation, and Fortran to the intermediate representation, and C++ to the intermediate representation. And then we have backends from the intermediate representation to x86 and Spark and so on. And so now we can write several front ends for a bunch of languages and several backends, and we have all the different combinations. So rather than writing n time m compilers to get all the combinations, we just write n front ends and m backends. It's a lot less work that way. And this intermediate representation, which a compiler writer would refer to with the shorthand IR, has another interesting thing we can do with it. As it turns out, a lot of optimization is completely language and machine agnostic. While we might do some optimization that's language specific in the front end, and we might do some optimization that's hardware specific in the back end, a lot of optimization can be done just using the intermediate representation and would work for all front ends and all back ends, and that's where a lot of the most interesting work is. And this is what compiler writers paradoxically refer to as the middle end. I'm not quite sure how something can be on the middle and be in the end, but in makes it sound important, so that's what compiler writers call it. And this is actually where we're going to spend most of our time throughout the series. This time, we'll dig a little deeper into how Java code specifically executes. As you'll recall from the previous segment, a compiler is made up of some front ends, which process the source language, a middle end, which works on intermediate representation and performs optimization, and back ends, which target different pieces of hardware, x86, Spark, ARM. Hopefully from this you already got a basic idea of how Java achieves write once run anywhere. We have different backends for x86, Spark, and ARM, so that your Java code can run wherever you need it to. But there's also a question of, what should this intermediate representation be? Java, of course, uses bytecode, which is a form of portable machine code. To make it efficient to interpret, it's basically linear in nature. But more sophisticated optimizations would require a graph-based intermediate representation. Unfortunately, graph-based intermediate representations are slow to traverse, so that's not what we start with. Specifically, when Java was first created, it only had an interpreter. So it was important to the creators of Java that Java bytecode be efficient to interpret. So the Java frontend, Javac, takes our Java code and produces Java bytecode, which is effectively an intermediate representation. And then we have a backend that is both an interpreter for execution as well as a JIT, a just-in-time compiler, which can target different pieces of hardware. But even once we've decided on that, there's a question of what type of representation do we want still? There are 2 popular choices. We could go with a stack-based representation, which is also known as zero-operand form, or we could go with a register-based representation, which is known as 3-operand form. And we'll see why they're called that in just a moment. As you may know, Java uses a stack-based implementation. So if we took the statement foo equals 30 plus 2, this is how it would look in Java bytecode. Here, you can see the bytecode on the left. The left column is our stack, and the line across the top are our local variables. So to add 30 and 2 together, we start by pushing 30 onto the stack. This is a bi push. It pushes a byte as an integer onto the stack, like so. For commonly used numbers, for efficiency of space, not execution speed, Java uses special instructions. So for 2, we have an iconst2. There are also special instructions for -1 to 5. And this pushes 2 onto the stack. Now the iadd. You'll notice that unlike the bypush, the iadd takes no arguments, but it's got to be adding two things together. Those are the two things on the stack. That's why it's called zero operand form. We don't have to specify our left-hand side, our right-hand side, or even our destination. It's implied. All of those things are the stack. We read from the stack, we write to the stack. Once that's done, we now have 32 at the top of our stack, and we use a special instruction iStore0 to store into the first local variable slot, which happens to be foo. And now our operation is complete. So it took us 4 instructions and 5 bytes to add 30 and 2 together. The nice thing about a stack-based R is it's really easy to take our abstract syntax tree from before and turn it into a stack-based bytecode. So going down the tree, we see equals, and when we see the equals, we first realize we need to evaluate its right-hand side. So we see the plus, and we realize we need to evaluate its left-hand side, 30. So we do a push 30 onto the stack. We come back up to the plus, and we go down its right-hand side, multiply. So we need to do its left-hand side. That's a push 3. Come back up, push 2, come back up. Now we can do our multiply, come back up again. Now we can do our add, and finally we can store into foo. In all likelihood, you're actually fairly familiar with what we're doing here. All this actually turns out to be is reverse notation. So it's very easy to take the tree traversal and turn it into a stack-based bytecode. And it's also pretty easy to write the interpreter for this. You just write something that looks like this, for get the next operation, well it's not null, keep going, and then we do a switch on the operation, popping our 2 operands and pushing our result. And then we have to do this for all the bytecode instructions. Before we delve too far into Java performance, we're first going to look at Java class files. A Java class file looks a little bit like this. It starts with the hex words cafe babe, followed by a minor version number and a major version number. Following the version numbers is the constant pool. The constant pool is a big heterogeneous soup of all sorts of literals that exist in the program. It's string literals, double literals, class names, method names, field types, all sorts of things. After the constant pool are flags, just a bit field of the various attributes that a class can have. So public, private, final, is an interface, those sorts of things. After that is this class. The this class is actually only 2 bytes, which is clearly not enough to store any arbitrary class name. This class is an index into the constant pool where we'll find the name for a given entry. Then we'll have a superclass and the interfaces. The interfaces are a bit interesting. If this is an interface that we're declaring, then this will be the extends clause of the interface. If this is a class, then this will be the implements clause of the class. So regardless of what we're declaring, all the interfaces will go in the same place. After the interfaces are the fields, followed by the methods, and then something called attributes. Random meta information about the class. So they could be debug information, they could be the source file, anything you like. You can actually make up a random attribute and embed it in the class file, and the class would still run. Attributes are the mechanism by which we've extended the class file over the years. They don't really have a functional purpose as far as the VM is concerned, but they can be used for things like generics, throws clauses, things like that, when we want to add some extra semantics to the file that the VM doesn't necessarily care about itself. And everything in the class file can actually have attributes, so fields and methods can have attributes too. Now let's look at some real examples of class files. Here's a hello world program that prints out the string hello world. I'm going to use a tool called JavaP that comes with your JDK to look at the contents of the class file. So I can do JavaP, give it the hello world class file that Eclipse has already compiled for us. And when I do that, I see the members of the class file. So I see my main method, but I also see the constructor, even though I didn't declare one. Remember, Java creates default constructors for us if we don't specify any constructors. There is a constructor there, even though I didn't type one in the example before. If I'd like to see the contents, the actual bytecode, I can do JavaP with the -c to show the code. And there's our Java bytecode. So we can see the main method at the bottom, and we can see the first thing is a get static to get the system out field. And then we do a LDC to load a constant, our string hello world, and then finally an invoke virtual to call the println function. And you'll notice next to each of these bytecodes is a number. These are actually indices into the constant pool I explained earlier. And if we'd like to see the constant pool, we can run JavaP with a verbose option, and it will show us everything. See, we got a lot more output. Here's our main method. Here's our code. It's also telling us our maximum stack size, local variables we use. There's a line number table and local variable table. These are attributes, which give us our debugging information. This is the constant pool. So we can find references to system out, which is the field that was referred to by our get static instruction. And we can find other things like the println as well. So you can see all the various contents of the file. Here's a simple example of a call. We have a main method calling a max function with values of 10 and 20. And then we have a max method, which is what you'd expect. Switch back to the command line and use JavaP with the -c option to see what the call class contains. So we can see our main method. The first two instructions are pushing our arguments onto the stack. So we do a bypush as an integer onto the stack, push 10, and then we do it again to push 20. That gets our two arguments on our stack, which are then consumed by our call. And since our max method is static, an invoke static is used to call the function. And then what's this pop about? We didn't actually use the result of our max call, but calling max did put the result onto the stack. And to make sure that the value of the stack stays consistent, a pop is inserted to remove that value. Even if you don't consume the value is still placed on the stack and consumed. So how does max receive its arguments? It receives them in the first two local variable slots. So local variables start at 0 for our variables x and y. So the iload 0, which is our first instruction, is loading x, and the iload 1, the second instruction, is loading y. And then we do an if. But we didn't write an if, we used the ternary operator. Turns out in bytecode it makes no difference. The interesting part here is that it's an if underscore ICMP LT, saying it's an integer comparison less than, although we actually wrote a greater than or equal. Here the compiler has actually flipped the logic from a greater than or equal to a less than, and it actually jumps conditionally to the else part, so the returning of y. So it's jumping to instruction 9. I can see that's an iload 1, so it's loading 1, and then we'd fall through and return it. If the condition didn't evaluate to true, then we'd pass the condition, we'd do an iload of 0, that's x, and then we'd go to 10 to return x. And now you can see how argument passing works. We push them onto the stack in main, and then they're just loaded into local variable slots, and we can load them from there onto the stack inside of our max method. And we'll look at one more example. Here I'm constructing a new object inside of main, and we'll look at the bytecode for that. Again, we'll use JavaP with the -c on our new class. So we can see there's a new instruction to construct our object, but this doesn't actually fully construct the object. This just allocates space for the object. So it's more like a cmalloc. We're just making room for the object. It's actually closer to a calloc. In Java, we're guaranteed that we won't get garbage values. We're guaranteed that our object will be 0 initialized. So that's the difference between calloc and malloc in C. Now, once we have a reference to our object, it's on the stack, we still have to invoke the constructor. And that's the instruction invoke special, which calls the magic method object.init, which is just object's constructor. Our constructor is actually in the class file called init in angle brackets, just like objects. But the real name of every constructor is actually angle brackets init. In this segment, we're going to look at the small number of optimizations performed by Javac. And it turns out it is a small number. With the introduction of HotSpot in Java 1.3, optimizations stopped being the concern of Javac and started being the concern of the just-in-time compilers. The first optimization we're going to look at is a relatively simple one called constant folding. If we have a simple expression that takes only constants, then we can pre-compute the value of the expression at compile time to avoid doing it at runtime. So here, I'm setting my kilobyte constant equal to 1 shifted to the left 10 times to compute the value of 1024. This is going to be computed at compile time and won't have to be computed again at runtime. To show you that that occurred, I'm going to use a Java disassembler called JAD. You can download JAD yourself, or you could use JavaP, but it's easier to look at Java code than Java bytecode. So to use JAD, I give it a class file, which Eclipse has already compiled for me. So I will give it our constant folding class file, and JAD will produce a constant folding JAD file, which contains Java source. And you can see my kilobyte constant is just set to 1024. There's no sign of the shift operation that I originally wrote. We can do something called constant propagation. So we've already computed our constant folding kilobyte constant, and we can build on that by shifting it left 10 times to calculate our megabyte constant. Even though this is a variable from another class file, because it's static final, it can actually be used as a constant here as well, and we can continue to do a constant fold. And we can actually do this for string literals as well. So we can actually form a megabyte message, which says 1 megabyte is however many bytes, and we'll see that that gets turned into a simple string literal. Again, we'll use JAD to disassemble the file. And we can see that 1 megabyte is shown as a hex constant here, and our megabyte message says 1 megabyte is 1,048,576 bytes. We can also use these constants to go one step further and do something called dead code elimination. So we can propagate a Boolean constant into an if and use that to either always keep a piece of code or throw out a piece of code, as we're doing here. So we have an always variable, which is true, and that will always print out always. And then we have a never variable that's false, which will never print out never. What we're going to see is that the if for always goes away, and we're just going to unconditionally print out always, and the never block, it just disappears entirely. So again, we'll use JAD to illustrate. And as you can see, our main method ends up containing a single printout of the string always. There's no printing out of never, there are no ifs. We just kept the if that's always true, and we threw out the if that's always false. Sometimes this constant propagation can actually be annoying, because it actually does propagate across class files. And if you want to be able to hot patch a class file, say to update a version number or something like that, maybe you actually don't want the propagation. One way to solve this is to make the variable not be final, but there is another solution. All it takes to confuse Javac is to put any sort of method call on the right-hand side. At this point, it's not treated like a constant anymore, even though it is set at technically class initialization time. So here, I'm just using the identity function to prevent my not propagated constant from being propagated, whereas the one that's assigned directly will be propagated. Again, we'll use JAD to demonstrate. As you can see, for my first constant that's propagated in the main, it just says system out println 32. There's no sign of how I got it. We don't know that it came from the propagated variable. But the other one, because an any function call will do, it does not get treated the same way. It is no longer eligible for constant propagation. Of course, that also means it's no longer eligible for constant folding. So you don't want to do this very often, but it can come in handy sometimes. As you might expect, some of these optimizations work for local variables as well. So here I have a local expression inside of a method, 10 plus 5. This will actually get folded. And you can see our 10 plus 5 was just turned into 15. But if we make this slightly more complicated, it doesn't work anymore. I could say int x equals 10, y equals 5, return x plus y, and this won't get propagated and folded. As you can see, the code remains unchanged. You might ask, could I make the variables final? Would that change anything? No, actually. Final isn't actually preserved in the class file at all for local variables, so making the variables final won't make any difference. In fact, JAD wouldn't even realize I changed anything. But I can do that, and we can verify that that's the case. So we'll run JAD again, we'll overwrite our source, and we'll look, and you can see JAD doesn't even know that those variables were final. That information is just not in the class file, not for local variables. Now, in principle, there's no reason that the Javac compiler shouldn't be able to do this optimization. The bytecode that we're going to produce from the x equals 10, y equals 5, return x plus y, looks like this. We do a by push 10, I store 0 to store into x, an I const 5, I store 1 to store y, reload the values and add them together. We could track the logical machine state of putting a 10 into the first stack slot, putting it into the first local slot, reloading it, and then when we get down to the add, know that the two values on the stack are constants and do the folding. We could do that, but when HotSpot was introduced, we made the decision that it's no longer Javac's job to do much optimization. It's the JIT's job to do the optimization. This is no longer done by Javac. It's left to the just-in-time compiler. In this segment, we're going to move beyond Java class files and the simple optimizations of Javac and start to look where optimization of our Java code really happens, in HotSpot and the just-in-time compilers. When we're talking about HotSpot and executing Java code, it's important to understand that Java code doesn't run in just one way. When our program first starts, all of our code's running in an interpreter, which is relatively slow. And as the interpreter runs, it profiles our code, trying to learn what we're doing all the time. Are we calling this method a lot? Are we not calling that method much at all? It attempts to learn from that so that it can decide where is it best to spend its time, what should it compile. And then we trigger the just-in-time compilers. And unlike C or C++, the just-in-time compiler can do some interesting things. It doesn't just do static optimization, it can actually make some educated guesses. Because in a managed runtime, we can correct those mistakes by de-optimizing and starting the process over again. To illustrate the HotSpot lifecycle, we'll start by running a simple program. This program allocates 1,000 objects at a time in inner loop and measures the performance using system nanotime both before and after the loop and printing out the difference. This whole process is done 300 times in outer loop so we can see how the performance changes as the application continues to run. Throughout this example, I've set up aliases for Java 7 and Java 8 so you can see how the behavior is a little different between the two VMs. I'm going to start by using the Java 8 alias with our simple program. And I'm going to pipe the output through less so it's a little easier to read. So we can see the left column here, the outer loop, represents one chunk of 1,000, and the right column is the time in nanoseconds, the difference between our two system nanotime calls. It takes about 40,000 nanoseconds to allocate 1,000 items, at least at the beginning. As the application continues to run, the numbers get better. Suddenly, it's taking about 10,000 nanoseconds to allocate 10,000 objects. And as we continue further still, the numbers will improve further. When plotting it, I noticed a couple large spikes, and those are GC pauses, which isn't terribly surprising because, after all, we are allocating a large number of objects. A more interesting pattern appears when you put it on a log scale. You could see it in the previous graph, but it's much more obvious when done this way. There's a first phase of execution. That's the phase where we were seeing numbers of around 40,000 nanoseconds, and that's the time where we were running in the interpreter. And then the just-in-time compiler kicked in, and our numbers improved to the 10 to 20,000 nanosecond range. And then finally, another just-in-time compiler kicked in, and our numbers improved even further still, down to that 40 to 80 nanosecond range. And when you plot it this way, that pattern really becomes visible. It was a little harder to see when the GC spike was dominating things. Now you might wonder, is the behavior the same in Java 7 or any other version of Java? And of course, the answer is no. Different versions of Java behave somewhat differently. To illustrate, I'll run the same simple program in Java 7. Immediately you'll notice all of the time measurements are multiples of 1,000. Turns out, on certain versions of Java, time moves in discrete increments. On my MacBook in Java 7, it moves in increments of 1,000 nanoseconds. Later releases of Java 8 have more accurate time, but this release of Java 7 only does 1,000 nanoseconds at a time. The values are right around 40,000, just like the Java 8 program. But when we scroll down, we don't see values of 10 or 20,000. It just drops immediately to 0. Why is that? In the Java 8 program, our final phase of execution was showing numbers of 40 to 80 nanoseconds. But in Java 7, we only have values that are multiples of 1,000. So if the clock doesn't move forward, we see a 0, or if the clock did move forward, we see a 1,000. But what this is really reflecting is that final phase of fast execution. But that's the only phase we see. We don't see that phase of 10 to 20,000. And so if we were to plot this, we'd see a profile that looked more like this. There's a short phase at the beginning running in the interpreter, and then a JIT kicks in, and our numbers are just unbelievably good. But there's more to the story. We can run Java 7 in another mode. In Java 8, they turned on something called tiered compilation by default, which was off but experimental in Java 7. So if I turn it on in Java 7 by using -XX:+ tiered compilation, and then run my simple program, now we still see those multiples of 1,000, but we start off with increments of around 40,000, and then we see that second phase, numbers around 10 to 20,000, before we reach the final phase of 0 to 1,000. And when we plot that run, our numbers start to look a little closer to what we saw in Java 8. We see an interpreter phase, we see a first JIT phase, and we see a second JIT phase. It still looks a little weird because of those multiples of 1,000 only. But when we overlay this on top of the Java 8 run, we still see a slight difference. The interpreter phases end at about the same point in time in both runs. But in Java 7, the final phase happens a little sooner than it does in Java 8. In Java 7, the second phase kicks in after only 125 iterations of the outer loop, as we can see from the blue line, Whereas in Java 8, it doesn't happen until close to the 260th iteration, as we can see in the green line. So there are still some significant differences here. So now we've seen the just-in-time compilers activated in both Java 7 and Java 8, and we've seen some of the differences. But what we haven't seen is the triggering of that final phase of execution, de-optimization. Well, it turns out with just a simple change, we can actually see that behavior as well. We'll start by adding a trap variable, which is initially set to null. And on the 300th iteration of the outer loop, we're going to set trap equal to something. And then in the inner loop, we're constantly checking to see if trap is not equal to null. If it is, print out trap, and then set trap back to null. The only difference here, this is going to print trap once on the 301st execution of the inner loop, and that is all. We'll run this program in Java 8, again piping through less for readability. Now we see similar numbers at the start, and then we see the phase change when the first JIT kicks in, and then we see another change in behavior when the second JIT kicks in. At the 300th iteration, the performance spikes. We could believe one high number happens just because of I/O, but that can't be why the numbers stay high after that, and it's not. The numbers stay high for a little bit, and then they start to come down again. What we've seen is de-optimization happening. What happened here is in our program, when the just-in-time compiler kicked in, at that point, the trap variable had always been null. So the compiler speculated that it always would be null. And when that proved wrong, on the 301st iteration, it had to correct its mistake. And it corrected its mistake by going back to the interpreter. And if we plot the numbers, the pattern becomes pretty clear. We see the top phase running in the interpreter, then our numbers come down to around 20,000. That's when the first JIT kicks in. And then the second JIT. Now, because the code's a little more complicated this time, it never got to quite the same numbers it did before. As we saw, it only got down to around 800 nanoseconds. And then when the trap occurs, we go back up to the level of the interpreter, and then we come back down to the first JIT until we finally come down to the second JIT again. And you can actually go around this cycle many times. And these are the types of behaviors we're going to explore further in this series. In the prior segment, we saw some concrete evidence that the VM really does transition from the interpreter to a first-tier JIT and on to a second-tier JIT. And ultimately, we're going to spend our time mostly talking about what the just-in-time compilers are capable of. But even before we get to the just-in-time compilers, the VM has some clever tricks. First off, the interpreter. You actually don't have one, at least not if your VM isn't running. What you have is a recipe for creating an interpreter. Your interpreter is actually dynamically generated when the VM starts up. To some degree, it's actually optimized for your hardware. And the interpreter is what's called a threaded interpreter. This reduces the amount of branching so that the interpreter can run faster. Even when running in the interpreter, the VM has something called intrinsics. These are special functions, often implemented in machine code, that will always run fast, even in the early phases of execution. And the VM has some clever lock optimizations that always apply. First off, let's see some intrinsics. As I said before, these are methods that are important, things like system array copy, or small and should be fast, that maybe the hardware has special support for, like math sign or cosine. And these are often written in assembly code, or in the internal representation of the just-in-time compilers, so they can receive special treatment by the VM. And HotSpot, it actually has more than 250 of these. Let's look at just one of them, system array copy. System array copy has a rather strange signature. It takes object, int, int, because object is the only common parent class of all the array types. While the JDK authors could have overloaded array copy to have a different version for byte array and int array and so forth, they didn't. So it just takes object. So how could it possibly be fast? Doesn't it have to do crazy type checks? Well, it might, but usually those can be compiled by the just-in-time compiler. But as it turns out, even running in the interpreter, it's fast, as compared to what you'd have to do yourself, copying the array inside of a loop. So let's compare the two and see if that's really true. First, we'll create an original array containing 100,000 random integers. And then to test copying by hand, we'll create a new array of the same size, and we'll copy each element one at a time, measuring the performance using system nanotime, inside what I'm calling the copy loop. And then we'll do the same operation using system array copy, and we'll compare the results. Running at command line, we can see that the array copy is over an order of magnitude faster than the copy loop, taking only 150,000 nanoseconds to run rather than 1.7 million nanoseconds to run. Now, maybe this got just-in-time compiled, but we can make sure that doesn't happen by using -accent, which instructs the VM to only run in interpreted mode. And we can see the results are much the same. But to make triply sure, we'll run with accent plus print compilation, which instructs the VM to print out any just-in-time compilations that it's doing. And the results are the same. The reason is, intrinsics are often implemented as machine code, or the internal representation of the compiler. And if they're implemented in machine code, they'll always run as machine code, rather than in the interpreter, which is much slower than the just-in-time compiler. Now don't get me wrong, the copy loop, in the end, it'll perform just as well as an array copy once the code gets just-in-time compiled. But why should we write more code than we need to? And why should we go slower, even if it's only in the beginning and for a short period of time? Now let's talk about some of those lock optimizations. The VM has many, but the ones that are done even in the interpreter are called bias locking and adaptive spinning. Bias locking is simple. We have a lot of classes that are synchronized, like string buffer, or input stream, or output stream. But typically, we only use them in one thread. So could we make it cheap for the same thread to keep requiring the lock, so that we don't have to pay this full cost for the append of foo and the append of bar? That's what lock biasing is. We bias the lock to the thread that just had it, and we make it cheap for that thread to take it again, at the expense of making it more expensive for another thread to take the lock. Let's see if we can make it happen. We'll open the bias locking example, which has a lock object, but we also need something to do inside the lock. So we have a sync variable, where we're going to put a new object each time. And then we also have a done variable, but I'll show you what that's for in just a moment. In a loop, we're going to lock 20 times. And lock simply creates a new object, and then assigns it to our sync inside the lock. This will bias the lock towards the first thread. And now we need to revert the bias. So we have an unbiased method that starts a new thread, that takes the lock, and sleeps for 5 seconds. And after it's done, it sets done to true, and it notifies. We start that thread, and then in our original thread, we synchronize on the lock, and we see if we're done. And if we're not, we wait. And since this should get there before the 5-second sleep is over, we should actually wait. And in the meantime, our lock will have been biased towards the other thread. And then we come back to the main, and we lock another 20 times. Now, I'm not printing out performance numbers just yet. We're going to see the lock biasing a different way. We're going to run this program at command line, but we're going to do it with an extra flag. Print safe point statistics. And we got a lot more output than we expected. These are safe points. These are points where the VM does cleanup work. And these are actually stop-the-world pauses. One type of safe point is garbage collection. But there are actually many others. But sadly, we haven't actually managed to exercise bias locking, because bias locking is not on at the start. The only interesting safe point that we see is the enabling of bias locking after a certain amount of time. But we can fix that by adding one more flag. Bias locking startup delay, and we'll set it to 0. Now we see 2 safe points. The enabling of bias locking, which now happens at the very beginning, and a revoking of bias. And these are both stop-the-world pauses. Garbage collection isn't the only thing that can stop your VM. We'll see more of these as we go on throughout the series. So what else can the VM do in terms of lock optimizations? Well, it can do something called adaptive spinning. The idea is, if a lock is short-held, spinning is a better strategy. While it wastes CPU, it allows us to recover quickly and take the lock as soon as it becomes available. However, if the lock is held for a long period of time, it's a bad idea to burn all that CPU. It's better to let the OS take responsibility and wake up this thread when the lock becomes available. It'll take longer to wake up, and in the meantime, the OS can allow another thread to run on this CPU instead. This happens through a process called lock inflation. Locks start in what's called a thin state, where they don't have an OS lock. And if they're held for a long enough period of time, they're turned into thick locks, which are backed by an actual OS lock, so that they can sleep and not take up processor time. This can also happen if another thread waits on the lock. In that case, the lock will also be promoted from a thin lock, a spin lock, to a thick lock, so that we have something to wait on. And of course, this process can also be reversed through a process called lock deflation. And guess what? That happens at a safe point. Now, there are more lock optimizations, but those are done by the just-in-time compiler. Those are things like lock coarsening, where we can say, why take the lock twice for each append call? Let's just take one lock instead. or lock elision, where the compiler can recognize that this string buffer is never used outside this method, so there's no need to lock at all. Before we can talk about those, we need to learn how to trigger the JIT in the first place, and that's what we'll talk about next time. In the prior segment, we learned some of the clever tricks that the VM has even while running in the interpreter. But now we're going to move on to the most important trick of the interpreter, triggering the just-in-time compilers. When running Java in HotSpot, there isn't a single phase of execution. We start off running in the interpreter, and the interpreter is profiling our code to determine which methods are hot and which are not. It's trying to find the hotspots. This is where the name hotspot actually comes from, and finding those hotspots becomes the basis for triggering the just-in-time compilers. We're going to again run a simple program, what is called the invocation counter of hotspot. Hotspot is what is called a method JIT, which means the standard unit of compilation is an entire method. And the simplest way to determine if a method is hot or not is by simply counting how many times it's been called. So here, I call a hot method 20,000 times inside of a loop. This will be enough to get the method in-queued for compilation, but it will merely be in-queued for compilation. The compilers are running in background threads, and may not necessarily get to the method immediately. To make sure that the compiler actually has time to compile the method, I sleep for 5 seconds at the end of the program. Recall from before that Java 8 has a mode called tiered compilation that's on by default, but I'm going to run with it off because it's a little easier to see the basic behavior. We'll come back to tiered compilation in more detail in the next segment. To see the behavior of our program, we're going to run with a flag called print compilation. This shows us the compiles that are actually occurring as they're completed, and then we'll run our invocation counter program. And you can see a few methods got compiled. The leftmost column is the time that the compilation completed in milliseconds since the VM started. And then the second column is a compilation ID signed in the order that the methods were in-queued for compilation. Then there's a set of flags. We're seeing one here, the %sign, followed by the method name and the method size in bytes. And you can see our hot method did in fact get compiled. And strangely enough, main got compiled as well, even though main is only called one time. We'll see what that's about in just a moment. The few other things that can appear in the compilation output, the flags in the middle, are the %sign, which we saw, which is what's called an on-stack replacement. What this is a loop compilation. So when you see that, you'll also see a loop bytecode index to the right of the method name. This is really basically just a line number, except in bytecode. You can also see an S flag, which indicates that the method is synchronized, a bang, which indicates that the method has a try, catch, finally construct, or in, which indicates a native method. There are a couple surprising things when it comes to reading this print compilation output. First, you may have noticed that methods don't have signatures in the output. So you can have two methods with different signatures, which are hard to tell apart in the print compilation output. As you can see here, I have two methods, Java NIO buffer position, but they have different sizes. So these are actually two different methods with two different signatures. The one that's 5 bytes is actually a wrapper around the one that is 43 bytes. But nonetheless, it can make the output a little bit confusing. Additionally, methods that contain synchronized blocks actually contain try-finallys. The way try-synchronized actually gets compiled is into the code on the right. First, the lock object is retrieved and stored into a temporary variable. Then monitor enter is used to lock the object. Then try contains the body of the synchronized block, and the finally block unlocks the object. So while you don't think you have an exception handler, if you have a synchronized block, you do actually have an exception handler. We just produced a new piece of machine code. How does this code actually get used? It won't get used until the next call. What occurs is a caller method attempts to call a callee method that's just been compiled. When that happens, it doesn't call the callee directly. Instead, it goes to a call dispatcher. And if the call dispatcher finds a piece of JITted code, it jumps to there instead. Otherwise, it goes to the interpreter. And if it does find a piece of JITted code, it caches that back into the caller method so that we don't have to do this dispatch logic again the next time. There are some methods that really only get called once in an entire program, or maybe once per thread, but they're still hot. Main is a good example, but we often see some type of event loop. For instance, in a server application, you're likely to have a method in each thread that's waiting for requests from the outside world and then responding to them. Or in a swing application, you'll have an event dispatch thread that's waiting for mouse events or keyboard events. And while these methods are only called once per thread, They are hot, and they are used for the entire duration of the program, so it'd be nice if they got compiled. To do that, HotSpot has something called on-stack replacement. When there's a loop that's hot, HotSpot can actually switch in the middle of the loop execution to a compiled version of the loop. Not the whole method, just the loop. And the reason this is called on-stack replacement is because we may have a stack like the one on the left, where we're running our event loop first in an interpreter, and then we switch midstream to running compiled code instead. And we may have to reverse this process as well. So the method is already on the stack, and while that happens, we replace it with a compiled version. In our prior example, we had a simple loop that just called a hot method, and we happened to notice that main got compiled at the end. Let's see if we can see that a little more deliberately. We're going to switch to a program called backEdgeCounter, which does basically the same thing, but now with two loops calling hot method. Will this result in two compilations of main? Yes, it will. So we'll run that program, again with minus tiered compilation with print compilation. And we see first one compilation of main before the first sleep, and then another compilation of main after the first sleep. They both have a %, indicating that they are on-stack replacements, and they occur at two different bytecode indexes, one at bytecode index 5 and one at bytecode index 37, representing the two different loops. Now, if you've read about JIT compilation before, you may have already known about both the invocation counter and the backEdge counter, the thing that triggers loop compilations. What you probably didn't know is they actually work together. You can imagine there are methods, they're not called a lot, but they have moderately executed loops. Say something like Arraylist index of, which maybe you don't call much, but you have moderately large collections, so it'd still be nice if the method got compiled. To illustrate, we'll look at a program called bothCounters. This program calls a cold method twice inside of a loop, so it will have a relatively low invocation count, 2. But the cold method calls a hot method 10,000 times inside of a loop. So the hot method will have a total invocation count of 20,000, which we've seen is enough to get our methods to compile. You might expect that cold method will have one of those on-stack replacement loop compilations because it has a hot loop, and that's likely to occur. And the backEdge count will actually be 20,000 in this case because backEdge counts are cumulative across invocations. But cold method will also be compiled in its entirety as well. And this happens because the way the JIT is triggered is not actually just the invocation count, or just the backEdge count, it's the sum of the two. We can see that hot method got compiled, and we can see that cold method did indeed have a loop compilation, but cold method also was compiled in its entirety. And that's because the sum of the two counters will be 2 for the invocation count, plus 2 times 10,000 for the backEdge count, to give us a total of 20,002, which we've seen is enough to get the method compiled in its entirety. So now we've seen all the counters. In the next segment, we'll look at how tiered compilation works, since that's now the default in Java 8. In the prior segment, we learned about the invocation counter and backEdge counter and how they trigger full method and loop compilations respectively. But we ran all of our examples with the flag minus tiered compilation. This is a new mode that was added in Java 7 and was experimental and is now on by default in Java 8. In the prior examples, you may have noticed, I just pulled this number 20,000 out of a hat, which I happen to know is enough to trigger the compilers. But I never told you exactly what the threshold was where the JITs are triggered. Historically, it's because there wasn't one answer. HotSpot is actually not one VM. It was two different VMs, a client VM and a server VM, which had two different compilers. The client VM had a compiler called C1, and the server VM has a compiler called C2. And these two VMs with their two different compilers were actually intended for two different purposes. And those two different purposes led to having two different thresholds for triggering their just-in-time compilers. The client VM has a compiler called C1. It was designed for swing applications. Now I want you to think about running a desktop application. When we're running a desktop application, we'd like our program to start quickly. And for that reason, C1 is a fast-acting compiler. It compiles code very quickly, but the code it produces is relatively slow, at least compared to its cousin C2 that we'll see in a moment. And to get the program to start quickly, we need to trigger the compiler quickly. So we compile with the sum of 1,000 invocations plus backEdges. This is pretty early. It doesn't take long to reach 1,000, and so we don't have to stare at the Eclipse splash screen for very long. there's what's called the C2 compiler, which was intended for server workloads. C2 is designed to be a slow-acting compiler, but as a consequence, it produces faster code, about 2 times faster than C1. And C1 was already a couple order of magnitudes faster than the interpreter. The consequence is it takes 4 times as long to compile the same method because C2 is doing some rather sophisticated analyses. C2 is what's called a profile-guided compiler. So it actually needs the interpreter to provide it data on all sorts of things. Like, did that if always evaluate to true? Did it always evaluate to false? What type did we call at that call site? And all of that takes some time. So C2 triggers with a sum of 10,000. We need some time to actually gather data so that C2 will have a good profile to guide its speculative optimizations. Now today, we're all actually using C2. If you're using 64-bit Java, you're using a server VM, and you're using C2, the server compiler. At some point, we realized maybe we could have the best of both worlds. Maybe we could use C1 and C2. And that's the idea behind tiered compilation. To get quick startup time, we go from the interpreter to C1. A little bit later than before, we now use a count of about 2,000. The numbers change a little bit from one version of Java to the next. And then with another 13,000 counts, we'll go to C2 for the things that are really hot. The hope is we get nice quick startup time with fast execution of the hottest methods. And this is what we saw with our simple program in the very beginning. We start off in the interpreter, and then a first JIT kicked in. That was C1, the client compiler. And then we saw things get faster still, and that was the second JIT kicking in, C2, the server compiler. It's actually a little more complicated than that. There aren't just 3 tiers. There are actually 5. They look like this. Tier 0 is the interpreter. That's where we start. Tier 4 is C2. That's where we hope to end, at least for the hottest methods. Tiers 1, 2, and 3 are actually all C1, but with different capabilities. Now the common workflow, it's what I just showed you. We start off in Tier 0, the interpreter. We go to Tier 3, which is C1, and then from there to Tier 4, which is C2. So what's the difference in these C1 tiers? Well, Tier 1 is actually C1 with no extra instrumentation, as it's called. So no extra execution overhead to figure out what the program is doing. Tier 2 is C1 with basic counters. So those are the invocation and the backedge counters that we saw in the previous segment. We need those if we want to have a way to promote to another tier. And then Tier 3 is actually C1 with basic counters plus detailed profiling. Remember I told you C2 needs instruction level data? It needs to know, did this if always evaluate to true? In this mode, C1 does that too. So C1 actually keeps track that this if was always true. In the old server VM, that was only done by the interpreter. Now it's done by the interpreter and C1. And that gives C2 the data it needs. So the common flow is actually to go from the interpreter, Tier 0, straight to detail gathering, with the hope that we can get to C2 pretty quickly. However, during VM startup, C2 may be relatively busy. There aren't a lot of C2 threads, and C2 takes quite a while to actually compile. So maybe the C2 queue's gotten pretty full. In that case, we don't necessarily want to gather detailed information because C2's not ready to use it. So instead of going to Tier 3, we go to Tier 2, which is C1 only with counters. And when those counters go beyond their threshold, they try again to move to Tier 3 if C2 is going to be ready soon, i.e. the C2 queue is not as full. And then ultimately we still get to Tier 4, C2. For a trivial method, we start in the interpreter, and if it gets hot, it'll get compiled by C1. It could be Tier 2 or, as shown here, in Tier 3. And C1 realizes during the compilation that there's nothing here that C2 would be better than C1 at. So C1 decides it will take care of it itself and actually just recompiles the method at Tier 1, which is C1 with no overhead. Detailed information actually adds 30% to the overhead. That's why we don't want to do it if C2's busy. And counters that overhead too. For this case, we just compile at Tier 1. The idea is, for trivial methods, C1 is just as good as C2. Our end goals for tiered compilation are actually Tier 4, C2 for complicated methods, and Tier 1, which is C1 with no overhead for simple methods. Let's see tiered compilation in action. Similar to the examples in the prior segment, I'm calling a hot method inside of a loop. It prints out the empty string, so it's not really doing anything, but it's enough to get the I/O machinery of the JDK compiled so that we can see what's going on. And this time, there are actually two loops. One loop that calls hot method 3,000 times, which will be enough to get C1 to trigger, and we wait 5 seconds. And then another loop which calls hot method another 15,000 times, which will be enough to get C2 to trigger, and we wait 5 seconds. This way we can see both phases. As with the prior examples, we're going to run with print compilation. But if you're running with Java 7, you'll need to explicitly add plus tiered compilation because it's off by default in Java 7. Again, I'll pipe the output through less to make it a little easier to read. We can see that the methods do start off getting compiled in tier 3. That's what this additional column is here. It's the tier of execution. We don't see anything in 0 because we start off in the interpreter, and that's tier 0. And we can actually see some cases of the behavior I was describing. We see object init get compiled here, 62 milliseconds into the run, but then almost immediately, we see object init be compiled again, this time at tier 1. So it was compiled first by C1, and this turns out to be the trivial case because object init only contains a single return instruction, and C1 decides that it can handle that itself. So it recompiles at tier 1 a mere 10 milliseconds later, and then it does this rather strange thing. We see this line that refers back to compilation 9, the tier 3 compilation above, and it says made not entrant. This is actually blocking access to the prior tier 3 compilation now that we have a better version. And if we scroll down further still, we can see some methods transition to tier 4. So we can see methods like string index of, tiered compilation, hot method, buffered write being compiled in tier 4. And when that occurs, we can also see the tier 3 version being made not entrant. This making of methods not entrant is important to the way tiered compilation works. What it's actually doing is locking access to the old version when a new better version becomes available. Whenever there's caching, we need some way to perform cache invalidation, and this locking mechanism is how we do it. So the caller method may have a cached call from before that pointed to the tier 3 version of the callee method, but the tier 3 version is locked. So that actually causes the tier 3 to redirect back to the call dispatcher, which will then find the new tier 4 version, and that can then be cached. So from now on, the caller method will go to the tier 4 version rather than the tier 3 version. This is how the promotion mechanism between tiers works. This time, we'll look at a few odd cases where HotSpot just absolutely refuses to JIT, no matter how hot it is. First up, we have an example of a very large method. What it's doing is really simple. It's just adding x to 1,000 over and over and over again. But other than that, our example is very much the same as before. We call the hot method inside of a loop 20,000 times, and we'd expect that it should get just-in-time compiled. But it doesn't. Let's see just how much bytecode that turned into. Again, we'll use Java P, and we'll give it our huge methods class. And you can see that turned into just over 8,000 bytes of bytecode. Let's try running this program. To get consistent behavior between Java 7 and Java 8, I'm going to run with minus tiered compilation, just because it makes the output a little easier to read, with the usual plus print compilation. And then we'll run huge methods. And we can see that huge methods main got compiled. It's one of those loop compilations we talked about before, but our hot method, it didn't get compiled. Now we can make it compiled by just removing a single one of these lines. It's not a coincidence that my example is 8,001 bytes of bytecode. Now let's try running it again. Now the hot method actually did get compiled, now that it's 7,996 bytes of bytecode. There's a threshold of 8,000 bytes beyond which the VM won't compile your method. It's just too big. If you really wanted to, you could turn this off. I'll put our example back the way it was before. We can find out the flag by searching through the output of java-xx : plus print flags final. This will show you all the various crazy options that you could set on your VM. I'm going to run it with dash version just so we don't get a bunch of annoying help output at the end. But we get a big table of possible things we could set. I happen to know the flag I'm looking for contains the string huge, so I'm going to find it like this. There's an option called don't compile huge methods that's set to true by default. So instead of using the default, I'm going to set it to false by using -xx : minus don't compile huge methods. And now our huge method did actually get just-in-time compiled. Fortunately, this doesn't really matter, but I have seen a system with a really awful code generator that actually did have a method that was about 7,800 bytes. So it was dangerously close to not getting compiled, and it was one of the hot methods in the system. The reason that hot method wasn't getting compiled already is because it violated another fundamental limit of the JIT. You can't have too many arguments. Here I have an example program calling a hot method 20,000 times inside a loop, but this time the hot method's taking arguments, 70 of them, and they're all longs, so they're 64-bit. This is too many arguments for the JIT. But my hot method is really boring this time. It's actually just returning the constant 0. It doesn't even use the values of the arguments. But HotSpot doesn't look very deeply in deciding what to compile, so it uses just some basic information like the size and the number of parameters to decide if a method is a good candidate for compilation. If it doesn't pass those criteria, it doesn't get compiled. Let's see that this doesn't get compiled by again running with minus tiered compilation and plus print compilation. This time you can see the hot method did not get compiled. It says compile skipped unsupported incoming call sequence not retriable. That's compiler gibberish for I just don't support calling it this way. And the not retriable says I give up. And you can see it actually did the same thing for main as well. That's because main tried to perform something called inlining, where it copies the body of hot method into it, and that didn't work either. So it also gave up on compiling the loop within main. Now these situations don't arise very often, but they can come up, mostly with code generators. But it also represents something that happens more often in the VM, dealing with an unloaded class. It can happen that we'll try to compile a method, or a loop, that refers to a class that has not yet been loaded. This is because, in Java, or at least in HotSpot, classes are lazy loaded. It doesn't have to be that way according to the language spec, but in HotSpot, that's how it is. We have an example, which has an inner class missing. Of course, right now it's not missing, it's right there, but we're going to remove it. We have a main that loops 20,000 times and tries to construct instances of missing, and we're going to catch a throwable because we're going to take the missing class away, which means it can never be loaded. It's just not going to exist. You can see my directory listing. I have my missing class, but I'm going to delete it. With it deleted, now my unloaded forever test, it can't find the missing class because it's missing. So now if we run it with the usual set of flags, we're going to see a rather interesting result. We see our main loop did get compiled, but it says out to the side, compile skipped. OSR starts with an immediate trap. What the VM's telling us is it compiled the loop, but the very first thing in the loop is a trap back to the interpreter. So there's no point in transitioning to this compiled piece of code because we're just going to go right back to the interpreter immediately anyway. So we're just going to stay in the interpreter. And again, it tells us this isn't retriable. There are some other interesting cases that arise from differences in Java bytecode and Java the language. For instance, the synchronize block. That actually compiles into two different bytecodes, a monitor enter and a monitor exit. Now because the synchronize block is always contained within one method, that means a monitor enter and a monitor exit, when produced by Javac, are always within one method. But there's nothing in the bytecode spec that makes it so. You could have a monitor enter in one method and a monitor exit in another, at least in Java bytecode. But if you do that, the JITs are going to refuse to compile it, because that's not something Javac produces, and that's not something they handle. As Java programmers, this doesn't really matter to us, but it does matter to the people implementing alternate runtimes on top of the JVM. They have to play sort of by the same rules as Java if they want to get good performance. So far in the series, we've used HotSpot command line flags to see what's going on inside, but that gets a little unwieldy. So this time, we'll set up a tool called jitwatch that allows us to see the same things, but in a nice GUI view. And then we'll set up a plugin for HotSpot that allows us to actually see the assembly code that's coming out of the just-in-time compilers, both at command line and in jitwatch. To get started using jitwatch, go to GitHub and find the jitwatch repository. Scroll down the page, you'll find some helpful links to the jitwatch repository, as well as some videos and slides about jitwatch. And you'll find links to download the appropriate jitwatch version for your JDK. You'll see here that there are versions for Java 1.7 and Java 8. You do need to download the right version for the VM that you're using. And while this says it's for OpenJDK, it will work just fine with Oracle's product distribution of HotSpot as well. Since I'm using JDK 8, I'm going to download the JDK 8 version. Once you've downloaded and extracted the jitwatch zip, you'll have a directory that looks like this. You'll have some scripts for running jitwatch in different ways and running demos, and you'll have some information on how to get started. The most helpful one is the quick start txt. Here you can see it tells us the options that we need to use when running the VM, and it tells us how to launch the jitwatch UI. Unfortunately, we're not quite ready to run the VM yet. You can see it says to run with -XX: plus print assembly. But to do that, we have to add an extra plugin to HotSpot. Fortunately, the creators of jitwatch have included some helpful directions on how to set up the plugin that we need. If we follow the jitwatch wiki link, we'll find a page that includes a sidebar of various information about jitwatch, one of which is how to build the HS disassembler. And when we go to that page, we'll find instructions for how to build it for Windows, Linux, and Mac OS. I'm using Mac OS. These directions do involve downloading the source of the OpenJDK, and then building a dynamically linked library and copying it into your JDK directory. But this will work even with a production version of HotSpot. It just requires a little bit of time. Once you have everything set up, we're ready to revisit some of the examples from earlier. This time we're not going to run it just with tiered compilation and print compilation, but we're also going to use our newly installed assembly plugin. To do that, I use Java plus tiered compilation plus print compilation. And before I can use the assembly plugin, I also have to use a flag called unlock diagnostic VM options, which lets me use some extra capabilities of the VM. And then I can specify print assembly and the program I want to run. And you can see it's printed out all the assembly code. But there's a lot of it, and it's not that easy to read, and we have to figure out which method each one of these is. And that gets a bit painful, which is why jitwatch is nice. So let's see how to use jitwatch to do the same thing. If we go back to our jitwatch directory, we can look at the quick start txt again, and find out what flags we need to use when running our program so that jitwatch will have the output it wants. As you can see, it's very similar to the flags I just used. We're doing unlock diagnostic VM options and print assembly, but we're also doing trace class loading, which is actually optional, and log compilation, which is similar to print compilation, but actually produces a structured XML file rather than a textual log. So we're going to run our tiered compilation program again with those flags instead. Now it still prints out a bunch of assembly, but it also generates a hotspot log file at the end. We've generated a hotspot log file concatenated with the PID of our running VM. And if we look at this file, we'll see that it does indeed contain XML. This is the file that we're going to provide to jitwatch as input. To view the log file, we'll start by launching the jitwatch UI using the launch UI script, ending with sh or .batch depending on your operating system. Once you've launched the UI, you can open the log file by clicking the Open Log button in the menu bar and clicking the hotspot log that we just generated. Jitwatch is actually designed to be able to actively monitor a VM as it's still running, so it doesn't just open the log file. You can tell it when to start and stop processing the contents of the log file as you wish. So I have to click Start before I'll actually see anything in the UI. Once that's done, I see now a list of packages. This will reflect all of the classes that were loaded since we ran with trace class loading. And I can also see that it's parsing information about the compilations that have occurred. Since I was using tiered, I see both C1 and C2 compilations. I can also decide to filter out uncompiled classes, which I am doing, or I can show all classes. I can also decide to do the same thing for members of a class. We'll look at our tiered compilation class, and we can see that its hot method did get compiled because it's showing up here. When we click on the method, we can see things about the compilation. We can see size in bytes, we can see the compile ID, we can see hotness and invocation counts, those things that I told you existed but you couldn't see before. We can see the address at which it was installed, we can see the compiler that was used, and various other information. And better yet, we can click this Try View button, and we can actually see everything about the method at one time. We can see the source code, if you've configured the source visibility. You can see the bytecode, and you can see the assembly code. And jitwatch will actually highlight the corresponding line in each pane. To get the source view to work, you have to go back into the jitwatch configuration, click Config, change your profile to default. Under source locations, add the folder where your Java files are. And you can also do the same thing for the directory that contains your class files as well. Without that, the try view would only show you the bytecode and the assembly code. The log viewer mode of jitwatch is nice if you're trying to figure out a non-trivial program, but jitwatch was also created as a tool to just experiment and learn how the VM works. Jitwatch has another cool mode, sandbox mode. which you can activate by clicking the sandbox button in the upper left. The sandbox acts like a mini IDE where we can load small test programs and see how they behave. So let's revisit our constant propagation example from before, the one that Javac couldn't handle. This time, we're going to do the same piece of code before, int x equals 10, int y equals 5, return x plus y, which we hope should turn into 15 when the JIT gets a hold of it. And to JIT it, we'll use the usual trick of calling the hot method 20,000 times inside of a loop. When we run this program, we hope that the assembly code reflects a 15. No loading of x or y, and no addition. So let's run it. Here we can see our source code, which I'm going to hide so it's a little easier to read the assembly. We can see the bytecode, Javac did not optimize, and then we can see the machine code. We can try to find where the add is by clicking it here, but jitwatch isn't finding it. But if we look closely, we can find it. Right here is returning from the procedure. And right here, this move of 0xf into EAX, that's loading 15. That's our constant result into our return register, and that's it. That's all our program requires. What's all this other stuff? That's for dealing with de-optimization and decompiling and things like that, which we'll talk about later in the series. But for now, let's make sure that 0xf really is what we think it is by tweaking our program slightly and seeing if the value changes. So we're going to change y to 10. Now when we run our program, we expect our 0xf, which was 15, to have changed into a 0x14 for 20. If we look at our assembly, 0x14 EAX. It has managed to perform this optimization inside of the JIT. And throughout the rest of the series, we're going to dig deeper into what can the JIT actually do. In the last segment, we learned about a tool called jitwatch, which is a GUI tool for letting us see what's going on inside the VM. And with the help of the print assembly plugin, we could actually even see the machine code being produced by the JITs. But most of us aren't used to looking at machine code. And what we really want to know is, does our Java code perform better? If I make this change, does it run faster? And so in this segment, we'll introduce a tool called JMH, which we can use to benchmark Java performance. Measuring Java performance is hard. If you'll recall back to our earlier introduction of the HotSpot lifecycle, we had a relatively simple program allocating 1,000 objects at a time, and it showed different performance depending on which phase of execution we were in. If we were running in the interpreter, it took about 40,000 nanoseconds to allocate 1,000 objects. Once the first JIT, C1, kicked in, it took about 10,000 nanoseconds. And then once the second JIT, C2, kicked in, it only took 80 nanoseconds. And you can see you'll get drastically different performance measurements depending on when you measure. Performance wasn't even the same between Java 7 and Java 8. Java 7 doesn't have a very accurate clock for system nanotime, at least on OS 10. So Java 7 would only report values of 0 or 1000, rather than 80 nanoseconds. So there was measurement inaccuracy depending on which version of Java we were using. And even a simple change would cause the behavior to regress. You have to account for all of these things when benchmarking your application. And while a tool like JMH won't necessarily eliminate these problems, it at least is aware of these problems. And it will make sure to do enough runs that we'll actually get a reasonable measurement. And it'll calculate an interval so that we can see what's the range of values, both above and below our average. That's why we want to use a tool like JMH. JMH is actually an OpenJDK project. Not only can you see the source code, but it is actually now the official way to benchmark OpenJDK and commercial hotspot. It's actually what the VM engineers use themselves, and it was actually created by a VM engineer named Alexei Shipalev, who also blogs a lot about these types of performance topics, and his blog is certainly worth checking out if you're interested in these sorts of things. Maven uses some rather clever tricks underneath. It uses annotation processing to rewrite the benchmark code that we're going to create, and the simplest way to use it is actually to just use a Maven archetype. Fortunately, they've included directions on how to do that on the webpage. So we can copy this line, and we can go to command line, and it'll set up a test project for us. We can then go into source main Java, and there's actually a sample benchmark already created. But it doesn't do much. It just contains a single test method with nothing in it. But you can already start to see a little bit how a Maven benchmark works. It's kind of like writing a JUnit test, except rather than annotating methods with test, we annotate them with benchmark. And then the harness takes care of running it for us. We'll build the sample benchmark. And once the sample benchmark is built, we'll have a target directory that contains a benchmarks jar. We can run that using java-jar benchmarks jar. It's not really benchmarking anything. It's actually going to fork the VM 10 times. Every time it forks the VM, it's going to do 20 warm-up iterations before it actually takes a measurement iteration. And then it's going to do 20 measurement iterations on top of that. And then it's going to take the average of those 20 measurement iterations across the 10 forks and give us a result. Instead of waiting for the sample to finish, we're going to jump in and write a JMH benchmark of our own and show off some of the other capabilities of JMH in the process. First, similar to JUnit, you can annotate a method with @setup to indicate that it's a method that set up test data for your benchmark. Here, I've annotated a method that's setting up a random group of integers. Using the parameter size, I actually parameterize my test by using an @param annotation, which I use to set up a list of 10, 1000, and 1,000,000 integers. And here's my method that sets up the array of integers. And then, of course, we need something to benchmark. So in this case, we're just going to benchmark how long does it take to sum up all of these numbers. 4 values of 10, 1000, and 1,000,000 for the array length. I compile my benchmarks. And then I can use java-jar and give it the benchmarks jar. But I actually have more than one benchmark. And you can see the estimated time for this is 46 minutes. We're not going to wait that long. Instead, I'm going to run with a smaller number of iterations. I've done that by setting up a main that specifies options for how to run this test. So I specify I'm going to have 2 forks of the JVM, only do 2 warm-up iterations, and 5 measurement iterations. To really be confident in the benchmark, you should run a higher number, which is why that is the default in JMH. But to be practical for demo purposes, I'm going to run with lower numbers of iterations. Now I can use java-cp with a benchmarks jar, so no longer using the default main. And then I can specify benchmarks, which is the name of my package, and our JMH demo. That'll run the main. And you can see we just have 2 forks with 2 warm-up iterations and 5 measurement iterations. But we will run this test for each of the sizes. Right now we're doing size 10, we'll then do 1000, and then finally 1,000,000. But this gives us a far more reasonable ETA of 30 seconds rather than the 46 minutes we had before. And there are our results. What are the units for this result? It says ops per second. That's not exactly right. Ops per second is actually how many times it ran the sum method in a second. So it says for 10, it did that 861 million times. And we'd expect this number to drop off linearly. So we expect a smaller number for 1,000 by several orders of magnitude, and then for 1,000,000, even smaller by several more orders of magnitude. But that's not what's happening. The reason for those weird numbers? It can't really change the behavior of the JIT, and the JIT's gotten a bit smart on us. And it's actually eliminated our sum operation entirely so that all 3 take the same amount of time, no matter the size of the array. But we can solve this. We just need to actually use the result of the sum operation. And we can do that in JMH just by returning it. Now if I clean and reinstall my benchmark, hopefully we'll see some numbers that make a little more sense. Now that we've learned how to use jitwatch to see the machine code and JMH to measure the performance of our Java code, next time we'll look at JIT optimizations more closely, using these tools to verify what really happens. In the last couple segments, we learned about some tools to help us delve deeper into what's going on inside of the JVM. And with those in hand, we're going to look at what the JIT really does, starting with what are called peephole and local optimizations, which as the name implies, are small optimizations. You've actually already seen an example of a peephole optimization. When we looked at Java C optimizations earlier in the series, we looked at an optimization called constant folding, which was one of the few optimizations done by Java C. Turns out constant folding is an example of a peephole optimization. They're called peephole optimizations because they look at a very small number of instructions at one time to do the optimization. So here we're just looking at 10 plus 2 and realizing that we have a constant, an operator, and a constant, and we can just turn that into a constant. And that's a peephole optimization that's looking at a window of 3 instructions. And you've actually seen an example of a local optimization already too. We looked at constant propagation in Java C, but we also saw that it actually is done by the JIT, even for local variables. But that's not actually why it's called a local optimization. The reason it's called a local optimization is because it's done within one block of code. You can see here, the reasoning's fairly straightforward when we just have x equals 10, y equals 5, return x plus y. We can turn that into 15. But what if we had a slightly more complicated example? Something like this, where we have int xy, but if foo is true, we set x equal to 10 and y equal to 5, else we set x equal to 20 and y equal to 10. Now it's not so easy to optimize the return statement at the end. If we had a sufficiently clever compiler, we could move the return statement inside the true block and turn that just into 15, and we could move the return statement inside the else block and turn that into 30, but clearly that requires a bit more cleverness than just doing constant propagation. And so when we're talking about a local optimization, we're talking about an optimization that just works on one block of code. So it's not even local to a whole function, it's local to just the if part or just the else part or something like that. Probably not what you expected local meant, and we're going to see that compiler writers abuse the term global as well later on. But let's move on to some examples we haven't already seen. Another example of a people optimization, one called strength reduction. The idea here is if we have an expensive operation, like division, which you may not think of as expensive, but is more expensive than, say, an add or a subtract, we could try to replace it with a cheaper optimization, like a right shift, if it would give us equivalent results. And it does give us equivalent results for the example we see here. Y divided by 4, if y is an integer, is the same as y shifted to the right 2 places. So we can actually make this substitution, and we'll see a little bit later, it does actually run faster. Now, something I hope is starting to become clear from some of these people optimization examples is that a lot of what a compiler does is really just pattern matching. If you think about a people optimization like constant folding expressed in a stack-based bytecode, then it would be a constant instruction followed by a constant instruction followed by some sort of binary operator, and we would just reduce that down to a constant. Even if it was expressed in, say, some sort of graph-based form, which we'll see is actually the IR used by the JITs later, it would just be a bin op taking 2 constants as input. So all this really is a regex. It's not that complicated. Well, maybe it is. How many of you have written in regex? I'm sure most of you. How many of you got it completely correct the first time? Handled every edge case? Probably not. And how many of you were able to debug it successfully later? Probably even fewer. Well, this is a problem compiler writers face too, and they're going to focus on the common cases. Given the choice of the 9 people that write a piece of code normally and 1 person who writes it a little bit strange, well, they probably tested the 90% case, and they made sure they optimized that one. Strangely enough, the person who's working hard to optimize their code and ends up writing it a little bit weird might actually produce suboptimal code because the compiler doesn't recognize it. Now, that's not so likely to happen for something like a people optimization, but as we get into more and more complicated pieces of code, it gets harder and harder for the compiler writer to account for all the different ways you may have written it. And because of that, compilers actually have a process called canonicalization, where they'll take something that maybe you wrote in a slightly strange way, and they'll change it into a form that's a little more normal, sometimes doing very extreme rewrites. But there are even simple cases, like we'll take x greater than or equal to 10, and we might turn it into not x less than 10. And you're like, well, how is that any simpler? That actually seems more complicated. And you'd be right. But it helps us with the next optimization we're going to look at, something called common subexpression elimination. Here's an example of x equals a times b plus c, y equals a times b times d. And we can see that there's a common subexpression a times b. So maybe we could avoid doing that multiply multiple times. We could say temp equals a times b, x equals temp plus c, and y equals temp times d. And we'll get equivalent results. And a compiler does actually do this optimization. Okay, but how does this canonicalization thing that I just showed you help with common subexpression elimination? Well, let me give you one possible example. I have a for loop where I'm looping over the contents of an array, and I'm accessing array sub I inside the for loop. Now, one of the nice things about Java is we get safety for free. We know that we won't go out of bounds on our array, or we'll get an array index out of bounds exception. Logically, that means there's some sort of check saying if I is less than 0 or I is greater than or equal to the array length, we have to throw an array index out of bounds exception. But the compiler can actually prove that neither of those things happen. One way it could do this, although we actually have an even more clever scheme, is we could take that I greater than or equal to array length, and we could say, well, that's really just not I less than the array length. Since we've already checked I less than the array length as our test condition for our loop, we know that that's not the case. And now it becomes easy for the compiler to recognize because it's the same test acting as a common subexpression. I know it sounds a little weird, but the compiler does this sort of thing all the time to make its reasoning easier, to make the optimizations easier. Now, it's one thing for me to say these optimizations happen, and to say that they're beneficial. But one of the things I want to do in this series is prove to you that they really do happen and that they are beneficial, at least in some small way. And so next time, we'll use jitwatch and JMH to see these people and local optimizations in action. In our last segment, we learned about some optimizations called people and local optimizations. This time, we're going to use jitwatch and JMH to prove that they actually happen, and more importantly, that they're actually beneficial. We'll start by proving that the optimizations actually happened at a machine code level using jitwatch. And we'll do that using jitwatch's sandbox mode so we can experiment. We can open the local optimizations example, which demonstrates the optimizations we saw in the previous segment. Here we have a program that's calling a hot method 20,000 times inside of a loop, but you'll notice there's actually no sleep afterwards, which we've typically done. That's because one nice thing about the jitwatch sandbox mode is it runs the VM with a flag called -background compilation, which actually causes the Java thread to wait for the compiler thread to finish after it enqueues a job. So we don't need to sleep to do the waiting, it's just done for us by blocking for the compiler. Now what's the hot method doing? Well, it receives a parameter x, which is just our loop index from above, and it takes x and divides it by 8 to calculate y, and it takes x and divides it by 8 and adds 10 to calculate z, and then we return y plus z. So we have a common subexpression of x divided by 8, so we're hoping to only see a single divide. Well, actually, we're hoping to not see a divide at all. Since we're dividing by a power of 2, namely 8, we can turn this into a right shift operation using a strength reduction. So this will become a right shift of 3 rather than a division by 8. Let's see if that all happens. Now when we look at the code, we can see this line that's annotated with idiv out to the side. And it's an SAR of OX3 and a register EAX. What this is a shift arithmetic right, 3 spaces, of the register EAX. So this is actually our division by 8. And indeed we only see one of them, so we've also done a common subexpression elimination. And then further down, we can find our add of 10, and that's it. Well, what about our adding of y and z together? Where is that? Well, that's actually the adding of EAX to EAX. What it's done is it's taken the common subexpression x divided by 8, and it's adding it to itself to get part of the sum of y plus z, but then we still need to add 10 to it to get our final answer. But we can clearly see it hasn't maintained our order of operations. The compiler feels free to move things around, and maybe that worries you, but it shouldn't, because your hardware does the same thing. Well, what happens if we change the code just a little bit? If we make it where it can't do a strength reduction, or it doesn't have a common subexpression, will the optimizations change? They should. Let's try it. Let's change our x divided by 8 to x minus 8, and we'll leave it at that. Now let's see what happens. Looking at the output, we can see that some things have changed. We still see our SAR shifted right of EAX, which we expect because we're still doing x divided by 8, we're just not doing it 2 times. But where's our x minus 8? Or where's our add of 10? They're here. You see an add of 2. What's actually happened is it's taken the minus 8 and the plus 10 and put them together into a single add of 2 in our final result. So here again, the compiler's found a way to reorder things to do less work. Maybe it's not common subexpression elimination, but as you can see, the compiler's still pretty smart, and it does these sorts of things all the time. Now the question is, does it actually make our code run faster? To answer that question, we'll turn to the JMH, measuring each optimization independently, starting with strength reduction. But we're going to measure things a little bit differently this time. I'm using an annotation benchmark mode and specifying that I want JMH to measure average time, rather than the default of ops per second. And I can also specify the time unit using output time unit. Since these benchmarks are going to run quickly, I'm going to use nanoseconds. And then we can test our strength reduction by having a benchmark where we divide by 4 and a benchmark where we divide by 5, the first one being able to use strength reduction to a right shift, and the second one not being able to do so. But we need something to divide, so I've created a variable x. But I want to make sure that I have the same value for x for when I'm dividing by 4 and dividing by 5 to keep this a fair test. So I'm seeding my random number generator with a constant value, so each fork of the VM will actually be testing with the same random number. We could of course make it change, and it wouldn't actually change our results, but this provides a more fair test. And every time you add state to a JMH benchmark, you need to add the @state annotation and specify a scope of benchmark so that that's allowed. Otherwise, JMH will yell at you. So let's see if this actually makes a difference. We'll run the benchmark. Well, as before, if we really wanted to be confident in these numbers, we'd need to actually run a lot more forks and warm-up iterations and iterations than I'm doing so here, but for demo purposes, that's just not practical. I assure you, I have run these a large number of times, and the results are consistent. There is a measurable difference, albeit a small one, but you really should actually use JMH's defaults most of the time. So what did we get? A div by 4 took 2.85 nanoseconds with a plus 0.03 error, and div by 5? It was dreadfully slower. It took 3.046 nanoseconds with a little more error. Well, that may not seem like much of a difference, but it is a constant difference of about a few percent. So why not do it? And just do it everywhere. It'll add up. Now, you and I as humans wouldn't want to do this. It's just tedious. But a compiler? It's easy for a compiler to do it. So it does. But the compiler can only do it if the divisor is a compile time constant. Otherwise, it can't do the strength reduction optimization. Let's try basically the same test again, but this time, rather than having two benchmark methods, a div4 and a div5, let's set the divisor using the parameterization capabilities of JMH. In this case, we won't be able to do the strength reduction because we cannot know at compile time what the value of divisor is, and we're always going to have to fall back to the slower strategy. And on top of that, we're also going to have to load divisor from a variable, so it'll take a little bit longer. Let's try this and see. And now we can see when the strength reduction doesn't happen, division by 4 and division by 5 take the same amount of time. And they both take an extra nanosecond and a half or so because we're having to do a load of the divisor. But now, they're equal. Now let's try something not quite so trivial. Let's try common subexpression elimination. To do this, I have a benchmark with some random integers, using the same seed trick from the prior two examples, this time with a helper method. And I have some variables, a, b, c, d, and e. A through d are all set to random numbers, but e is set equal to b for reasons you'll see in a moment. To test the elimination, first, we'll say x is equal to a times b plus c, and y equals a times b times d, and then we'll return x plus y. And we'll compare it to doing the elimination manually because we expect that it should perform the same. We'll say a temp equals a times b, x equals a temp plus c, and y equals a temp times d, and we expect that these two should perform the same. And lastly, we'll do an example that has no elimination. We'll do a times b plus c, but y will be a times e times d. Remember that b and e are the same value, but because they're different variables, the compiler is probably not going to be able to get the same performance. There is a difference here, but it's probably not going to be as much as you expect. You think, there's a load there. Isn't that going to be another 1.5 nanoseconds? Let's find out. And what did we get? Well, the elimination and the manual elimination versions, they're both coming in at about 3.2 nanoseconds. I assure you, if you run the benchmark enough times, they're basically even. And the no elimination version, it's 0.1, sometimes as much as 0.2 nanoseconds slower. But that's really not that much. Aren't we doing an extra load and an extra multiply? Aren't those going to be a little more than just 0.1, 0.2 nanoseconds? I thought this was an optimization. Well, it is, but for simple cases, it doesn't always matter, and I'll explain why. The problem is, it's not just our compilers that are smart. Our hardware's smart too. And our hardware doesn't actually do just one thing at a time. Well, of course, we have multi-core chips, but that's not what I'm talking about. Even a single core on a relatively old processor, like the original Core series of Intels, could do many things at once. Our instructions are given to what's called a scheduler, and this isn't a scheduler like your OS thread scheduler. Well, it sort of is, but its job is actually to schedule individual instructions to multiple threads of execution called ports. The hardware doesn't do a single add or a single multiply at a time. Each of these ports can do different things. So here you can see that ports 0, 1, and 5 can all do arithmetic logic. And then some of them specialize, like port 0 does floating point multiply and divide, and port 1 does floating point add. And so we can actually do multiple add instructions at the same time, or multiple multiply instructions at the same time. And so getting rid of the extra multiply doesn't always result in faster performance. Now, in the end, it will free up an execution port that maybe we can do something else with, so it's worth doing. It's usually not going to hurt us, but it doesn't always help us. But what about memory? Isn't it slow to go to main memory on a modern piece of hardware? It is. It can actually be dreadfully slow. If we go out to main memory, it will cost us 30 clock cycles plus 50 nanoseconds. Why didn't the extra load of E cause us to have much slower time? Well, memory is loaded in cache lines, and the variables A, B, C, D, and E were all likely to be in the same cache line. So as soon as we loaded A, we loaded everything else. The extra load of E doesn't cost us anything either. And so the extra load and the extra multiply, in the end, we get them almost for free. That's why, despite the fact that we'd expect the no elimination benchmark to be slower, and it is, it actually runs at almost the same speed. And for these sorts of reasons, a lot of these optimizations, while they could be expressed in intermediate representation, actually happen in the back end of the compiler. Whether or not a strength reduction is a good idea really depends on your piece of hardware, and those sorts of things happen to be done in the back end. Local optimizations are probably still done at the IR level, but not always. But those are the small optimizations. Next time, we're going to move on to the bigger ones, global optimizations. These are the non-local optimizations, but we'll talk about what that means next time. This time we're going to move on to looking at larger optimizations, what are called global optimizations. Here's an example of a global optimization, one called loop invariant hoisting, also known as loop invariant code motion. In this case, we have a for loop that's your standard C-style for loop ranging from I equals 0 to I less than the array length, incrementing I. But in Java, we know that an array's length is constant. Once it's created, it can't change. So the value of array length is always invariant, so that also means that it is loop invariant. It doesn't change over the duration of the loop. So perhaps we could optimize by pulling array length out into a local variable and then comparing against the local variable rather than having to reload the array length every time. Let's see if that does improve performance. To try and see if this optimization matters, we'll run a JMH benchmark, one called loop invariant. This benchmark sets up an array of random integers of size 1000, and then it proceeds to sum up the array using a C-style for loop and a hoisted version like we just saw on the slide, and also uses the enhanced for loop added in Java 5, just for comparison's sake. And in all three examples, we make sure the code is not dead code eliminated by sending the sum to the black hole. Let's see how this performs. And we can see in all three cases it actually took the same amount of time. But that's not because the hoisting is a bad optimization. It's just that the VM already knows how to do this optimization. And as we'll see later, our attempting to do it by hand can actually backfire. But let's see a few more of those optimizations. Another type of global optimization is something called loop unrolling. Imagine we have a small loop body, something like sum plus equals the array I. Would it be more efficient rather than just doing one of those at a time to do 4 at a time? Is that possible? It is possible, and we can prove it, this time not by using JMH, but by using jitwatch and actually looking at the machine code. As we've done in the past, we'll use jitwatch's sandbox mode to see the generated machine code, this time looking at an example called loop unrolling. Here we have a main method, which sets up a random array of 1000 integers, and then sums them up 20,000 times inside of a loop to make sure our hot sum method gets just in time compiled. And the hot sum method is simply using an enhanced for loop, but whichever type of for loop you choose, you'll get similar results. Let's run this and see what's generated. In the try view, we can actually see the assembly code, and we can see a lot of adds, not just one add for our loop. Our loop body contains 16 adds. It may just be coincidence, but that would be enough to fill a complete cache line on my x86-64 machine. And then below, obviously we can't just deal with loops of size 16. There's handling for any overflow, any extra iterations beyond a multiple of 16. So this loop unrolling will work even if our loop isn't a perfect multiple of 16. Now getting this sort of loop unrolling right is tricky. In fact, on modern Intels, it's really tricky. If the loop body is small, then you actually shouldn't unroll the loop, provided it doesn't have any branches or certain other types of hazards. But if those conditions fail, then you actually should unroll the loop. And because getting this sort of thing right is hard, the compiler will actually second guess you. Some compilers actually contain something called loop re-rolling, where they'll see that you actually tried to unroll the loop yourself, and they'll actually assume you did it wrong, turn it back into a regular loop, so that they can then unroll it in what they think is the better way. This seems crazy, and to be honest, it is a little bit, but it's really just another form of canonicalization. We take slightly strangely written code, turn it back into something that's easier for the compiler to recognize, and then proceed as normal. As it turns out, HotSpot actually doesn't have a loop reroller, but it may someday. As we just saw with the loop unrolling example, oftentimes compilers take our code and actually make it bigger. But they do this in the name of performance. But of course they have to be careful. They do this in some strange situations. For instance, imagine this piece of code. Boolean debug equals logger is debug enabled. Loop through some values. If debug, log the value. A compiler may well actually perform a global optimization called loop unswitching, where it says, because I know debug is a local variable and it's loop invariant, maybe I could actually get rid of that if inside of the loop by testing the variable first and then making two different loops. One that assumes the variable is always true, and another one that assumes the variable is always false. A compiler can actually do this. Obviously, it results in more code, but it results in faster code, so it's generally a good idea. At this point, you're probably asking yourself, what's global about any of this? Everything I've shown is limited to a single function. Yes, that's true, but that's not the way compiler writers use the words local and global. Local means local to a block, like just the if part of the example here. So if foo x equals 10, y equals 5, that one block, x equals 10, y equals 5, is a local region. The whole function, or actually even beyond that, is what is called global, anything that extends past a block. The way the compiler writers view this is they think about this in terms of a control flow graph. So we have an if foo, and then we have two blocks, x equals 10, y equals 5, x equals 20, y equals 10. And we have control edges, one that's true and one that's false. Those are forward edges, and each of the nodes are what are called basic blocks. Local optimizations are optimizations that occur inside of a single basic block. Global optimizations occur across the whole graph. Not exactly the definition you were probably expecting, but that's how the terms are used. And if we extend this a little bit further, we can actually understand why the counter in the very beginning was called the back edge counter. If you think about a simple loop, you would have a for loop with int I equals 0. That's one block. And then that would go to a testing block, I less than the array length. And if that evaluates to true, we would go down into the loop body, and the end of our loop body would be the incrementing of I, which branches backwards, a back edge, rather than a forward edge, to our test condition. And that's where the name of the counter comes from. Now we have a sense for some global optimizations, and we're going to start to try to actually look at a real piece of Java code, Arraylist forEach, which takes a consumer object. Now you might think that the implementation of Arraylist forEach would look something like this. For int I equals 0, I less than the size of the array list, consumer except this element sub I, but it doesn't. And to understand why, we're going to have to dig a little deeper into compiler concepts. But to give you a little hint, we'll go back to our loop invariant example from before, but this time with a slight twist. What's the twist? It's the placement of our black hole consume. Before, I was accumulating the sum of them, and I was placing the black hole consume at the end. This time, I'm placing the black hole consume inside each of the loops. For a C-style loop, a hoisted loop, and an enhanced loop, just as before, and also one that I call fully hoisted, where rather than using a reference to the member variable, I store a reference to the member variable locally, and then I do the same thing for the length. Now you might think from before that all of these would perform the same, but they don't. Let's see the numbers. Here's the results of running this benchmark. First off, we can see that the time in nanoseconds is much higher. That's because black hole consume is a relatively expensive operation, and that's making our numbers tenfold higher. But let's look at the values relative to each other. We'd expect the C-style, the enhanced, and the hoisted versions to all be the same, but actually, the enhanced is the fastest, and then the C-style, and then our hoisted version before, which I told you was a good optimization, is actually the worst. And that may seem bad, but then you look at the fully hoisted, and you see it's tied with enhanced for the best. Why is this? Well, for that, we're going to need a little more compiler knowledge. So next time, we're going to start looking at some of the concepts that underlie a compiler's reasoning, that allow it to decide what is a valid optimization, starting with something called data dependence and static single assignment. Last time we looked at some of the larger optimizations that can be performed by a just-in-time compiler, or really, any compiler. But to understand some of the stranger results we got at the end, we need to dig a little deeper and understand a few more compiler concepts. We're going to have to learn about something called data dependence graphs, and a curious thing called static single assignment, which is also known as SSA. We'll start by revisiting the example from before. We saw when we first started using JMH that if we had a benchmark of a function like this, where we don't return sum, it doesn't matter how big our values array is, it always runs at the same speed. And I explained that the reason this happens is because if there is no use of sum, this whole thing just isn't necessary. It's dead code, and it can be removed. But let's verify one more time that that really does happen, this time using jitwatch. Once again, we'll use the sandbox mode of jitwatch, this time looking at the revisiting dead code example. To approximate how the JMH benchmark works, I have a main creating an array of 1,000 integers, and then I call hotsum 20,000 times inside of a loop. And of course, hotsum doesn't return a value. Let's run it and see what the assembly looks like. Now looking at the assembly, there's maybe more here than you were expecting from my explanation. What's actually happening here is some bounds checking and some null checking that's just required by the language. But let's try highlighting the plus equals in our loop. That highlights an iLoad here, but there's no matching add to be found in the assembly code. In fact, there's no real loop to be found. We can find a little bit of branching, but no backwards branching. We just do a few tests here, and ultimately we just jump to a return. There's no add anywhere along this path. So the loop just got eliminated. To satisfy ourselves that that's really true, let's add a return and see if it looks different. Now let's see if we can find that add. Again, we click here, and now we can see that our loop got unrolled as we saw in the previous example. We have a whole bunch of adds for a whole bunch of iterations that have just been unrolled into one big block. That's quite a change. How does the compiler know to do this? And when can it do this? Are there situations where it can't? That's what we're going to start to look at. Let's think about the Java equivalent of the loop unroll code for a moment. It would be something like this. Here I'm assuming an array of size 4, but obviously we could go higher. So we have sum plus equals this values dot 0, 1, 2, and 3. And then there's nothing after that. The way the compiler approaches this is to actually version the sum variable to make Java code that looks like this. And sum equals 0, sum 1 equals sum 0, sum 2 equals sum 1, and so on. And the compiler actually does this. It goes and creates, at least conceptually, lots of local variables, a new version for every single assignment. While you may think programming without side effects is difficult, at least on some level, that's what your compiler is doing. It does what is called static single assignment. It assigns a variable once and only once. But how does this help with dead code elimination? Well, we can now look and see if each variable is used in a very simple way. Tracing from the end of the function, no one used sum4. And since sum4 was the only user of sum3, no one used sum3. And since no one used sum3, no one used sum2, and so on. And then we can dead code eliminate the whole thing by working backwards and seeing if there are any uses of these variables, any uses of these actual changes to our sum variable. And that's easy because we've done this versioning. Otherwise, the reasoning would be a lot harder. But if we introduce a single use of sum4, like a return, then now we keep the whole chain by the same line of reasoning. And this is how the dead code elimination for our loop works. But of course, this only works if the thing that we're eliminating doesn't have any side effects. It doesn't change shared memory in any way. Imagine our statement was just int sum equals the sum of the values, calling sum a function. Well, we could get rid of our store of the sum variable, but we can't get rid of our call to the sum method because we don't know what the sum method is doing, at least not without probing deeper. And so the sum call has to be kept around, even if we don't have to do the store to local memory. And that starts to hint at why Arraylist forEach is written the way it is, and why the black hole consume in our loop invariant example from the last time did not perform quite the way we expected. But to fully understand that, we'll have to keep probing. When we're considering this static single assignment variable versioning thing, there's a question. What happens if there's a conditional? I have if foo version 0, and if that turns out to be true, down one path I have x version 0 equal to 10, and y version 0 equal to 5. And down the other path, I guess we'll call this version 1, so we have x version 1 equals 20, and y version 1 equals 10. And then after the if, we have return x plus y. Well, which version of x are we using? And which version of y are we using? This seems to be a bit of a problem. And this situation is something that compiler writers worry about enough that they actually have a name for it. They call these diamonds, and you can see why. Looking at this control flow graph visually, it forms a diamond shape. The solution is something called a Phi function, or what was originally called a phony function, because it's not really a function at all. It's just another type of thing that the compiler can't optimize, at least not easily. Just like we couldn't optimize the call from earlier, we can't optimize the round phi functions either. So what does this phi function do? Well, in our bottom block, we introduce a phi that selects between x0 and x1 and creates a new version x2. So basically it just models the if. But since we don't know which path we took, we can't make assumptions about which x we used. And maybe this all seems a little wasteful with all these extra local variables. But at the end of the day, they will all be turned back into a single variable, or at least a single piece of memory, by the register allocator of the just-in-time compiler. This just helps with the compiler's reasoning. But for the moment, we're stuck with this line that we can't actually optimize past, which means we can't move our return up. If we could remove our return of x plus y up, then we actually could have optimized both of the blocks above. Unfortunately, that doesn't happen. But it's not the end of the world. It's not that the compiler can't do anything here. We can still deduce some facts. For instance, that since x sub 0 was equal to 10 and x sub 1 was equal to 20, that implies that x sub 2 is greater than or equal to 10. And we could actually still use that if the last part of our block was actually something like if x sub 2 is greater than 0 to deduce that that's always true, and the other branch just never happens. And this is another form of dead code elimination, this time working forward on the graph rather than backwards. The just-in-time compiler can do this as well. But let's see what actually happens for the simple example, the one with the return. Again, we'll use jitwatch's sandbox mode, this time with a hot method that resembles the one I just showed you. If foo x equals 10, y equals 5, else x equals 20, y equals 10. And we'll provide the value of foo at first using I mod 2 in our hot loop. So half the time it'll be true, and half the time it will be false. Let's see what happens. Here's our assembly code. This is some curious looking code. What's going on here? There's a move of OX14, that's 20, and there's a move of OXA, that's 10, into two different registers, EAX and R11D. And then there's a C move in E based on a test of ESI. ESI is foo. What is the C move in E about? And why have we already loaded both values for X, 10 and 20? Well, I told you, we may make multiple local variables. And if we have enough registers, there's maybe two versions of X at the same time, and that's what it's done. And then it uses the C move to pick between the two different versions. This is effectively our merge, our phi. Interesting. And then it does the same thing for Y, and it adds the results. I find this a bit curious, since we're effectively doing two branches instead of one, which doesn't seem very optimal, but this is what the compiler's chosen to do. But that was with a 50-50 distribution. Would changing the probability change the assembly? Let's find out. We'll change our probability to 1 out of 10. So 1 out of 10 times it will be true, and 9 out of 10 times it will be false. And then we'll run again. And our code does look quite different. And this may seem strange, but this is again something a compiler does. C2, the server compiler in HotSpot, is a profile-driven compiler. So it will make different decisions based on how common it thinks a branch is. If one path happens 90% of the time, it's going to try to optimize for that. If they're both equally likely, it will try to optimize for that. Although, in that situation, there's not a whole lot it can do. And so, even for the same piece of Java code, subtle differences in execution can have big differences in the machine code. This time we're going to continue to look at what a compiler can do using SSA form. First, we saw some basic control flow graphs last time, but we didn't see a loop. How do we make SSA work with loops? For a loop, we'd have a control flow graph that looks like this. Int I equals 0, I less than the array length, do something, increment I. When we add SSA and Phi functions, it will look like this. Int I version 0 equals 0. Int I version 1 is a merge, a phi, of I version 0 and I version 2. I1 is less than the array version 0 length. Do something, I2 is equal to I1 plus 1. And then we feed I2 back into the top of the loop, the test condition. So I1 is actually a merge of the value coming into the loop initially, I0, and effectively every iteration of the loop. And the compiler will actually run over this graph a few times and try to figure out what is the actual range of I1, but we'll see that a little bit later. What else can we do with this SSA thing? Well, remember when we talked about common subexpression elimination earlier? Common subexpression elimination hinges on knowing that a variable hasn't changed. So by versioning our variables, it becomes very easy to actually identify common subexpressions. Except we don't call it that. We actually call it global value numbering. The techniques are slightly different, each have their own strengths and weaknesses, but HotSpot actually uses value numbering, not common subexpression elimination. So what is value numbering? Basically, whenever we encounter a computation, we store it in a cache. We hash the inputs and the operand, and we store it in a cache. And if we see the same inputs and the same operand again, we go and see, is it in the cache? If so, we'll reuse that piece of code. And it actually is put into a graph that looks like this, with lots of little nodes. At least this is how HotSpot does it. So when we do the multiply here of B version 3 and C version 2, the first time we'll have to actually create that subgraph and put it in our cache. And then the next time we'll find it and we'll reuse it. And that's how we get to subexpression elimination. It sounds complicated, but it's actually quite easy to implement. And this graph, as you see it here, with all these fine-grained nodes, is actually closer to the representation that HotSpot uses. HotSpot uses what's called a sea of nodes intermediate representation, but it's a little visually busy, so typically I will just show you the basic block control flow diagrams because I think they're a little easier to understand, and conceptually there's not much difference. So we know this example works, but can we do this for non-locals? Is this allowed? It is allowed. Without a synchronizing action, as the spec calls it, there's no requirement that we reload a value. But there is a requirement that changes in this thread are always visible. And that first caveat allows the compiler to do some interesting optimizations, and that second one actually causes the compiler a lot of headaches. So it is possible, with a piece of code like this, to turn the multiple loads of p.x into a single load of p.x, and the multiple loads of p.y into a single load of p.y. This is allowed by the Java memory model. Let's see that this actually happens using jitwatch. Again, we'll use jitwatch's sandbox mode, and we'll load the redundant loads example. Here you can see I have a point class with members x and y, and I calculate its distance inside of a hot loop. We'll run this and see what the assembly code looks like. Now you can see in the bytecode there are two loads of get field x and two loads of get field y, and that makes sense because we did p.x, p.x. But if we actually look at the assembly code, we'll see there's only a single get field x and a single get field y, and they're both loaded, and then x is multiplied by itself to get our p.x squared, and y is multiplied by itself to get our y squared, and then they're added together. So there's only a single load of x and a single load of y. This does mean that this thread may not see a change to x or y, because we don't have a synchronizing action. If we wanted to make sure that we always saw updates to x and y, we'd have to synchronize in some way. And for a single field, the easiest way to do that is to make it volatile. For two fields, this is a little dicey, but for example purposes, we're just going to make the fields volatile. So we'll do that, and we'll run again. And you can actually see the bytecode hasn't changed, because it's a property of the field itself. It's how we get the field that's changed. The actual bytecode instruction has not changed, but the assembly code has. There are now two loads of get field x and two loads of get field y. We have to keep both. We have to see the latest value, but that's not required unless we make the field volatile. Okay, so we can fold two p-axes of p.x into a single axis of p.x. How far can we take this? Can we do this for loads inside of a loop? Do we have to keep reloading this.array over and over and over again? Twice per loop iteration, one to access the length and one to access the element? No. If we know that this array does not change, and that's important, then we could move it into a local variable, and then our control flow graph would look like this. Array version 0, check its length, array version 0, access its element. And you've actually already seen this happen, but you may not have thought about it. When we did loop unrolling, you saw this occur. I'll show you again. Again, we'll use jitwatch's sandbox mode, and we'll open an example called Revisiting Loop Unrolling. This is similar to our loop unrolling before, but with one critical difference. Our integer array is now a member variable, and we're calling a member function rather than a static function. Now I could continue to use the shorthand and just say int x in ints, but I want you to actually think about what this code really is. It's this.ints length and this.ints I. And so we are using a pointer to access our integer array, and this would require reloading. This is not a local variable, but that doesn't happen. Just like p.x, we can fold these into a single load. Let's see. If we find the get field and we look at the assembly code, we can see there's only one load. We can't find the other load. It doesn't exist. We just need to load ints once, because we know it doesn't change during the loop, and that's critical to allowing the loop unrolling. Here you can see we're doing this address calculation based off R11, which is a reference to our array, and we don't have to reload every single time. So to do loop unrolling, it really does require that we do this. We could reload each iteration, but that wouldn't help so much. With those examples, hopefully you're starting to get a feel for the interplay between the memory model and Java optimization. And maybe you're starting to realize these optimizations have some interesting implications for concurrency, which is what we'll explore next time. Before we move on to our next compiler concept, let's take a moment to consider the concurrency implications of the types of optimizations we've seen so far. As you're probably aware, writing concurrent code correctly is hard. But why is it hard? It's hard because of the types of optimizations we've seen so far. Code motion can move our code around, and things don't happen in the order we think they do, even relative to each other, and that can make writing concurrent code hard. And this can happen in the hardware too. There's actually out-of-order execution in the hardware, so that's just another form of code motion, and that makes concurrency hard. And the compiler can eliminate loads, so that values that we think we've loaded and we're going to see an update to won't be visible, and that makes concurrency hard. And the compiler can even get rid of stores. It doesn't have to store every single value if we don't use it, and that could make concurrency hard. Let's return to our load elimination example. We saw previously that p.x can be loaded a single time, as can p.y. But even this simple optimization, which seems correct, has some surprising implications. It requires us to give up a property called memory coherence. This actually was a property that we were supposed to have in Java 1.4 and earlier, although the just-in-time compiler never actually implemented it. What is it? Well, coherence is a guarantee that a thread cannot see an old value for the same memory location after seeing a new value. And when I say same memory location, you can basically think the same field of an object. This seems reasonable. This thread sees a value, it then sees a newer value. How can we go backwards in time? I'll show you. Here's how we can achieve time travel, and it follows directly from the load elimination we saw before. We have int I equals p.x, and then we have int j equals q.x. But it just so happens that p and q both refer to the same point object. That is, the same field of the same object. So it's possible for the first read of p.x to see a value of 100, and before we run q.x, the value could be changed by another thread to some other value, say 125. And so j is 125. But what about k, which is set to p.x? Well, since we can do redundant load elimination, that means that it is okay for k to see the original value of 100. And now we've traveled back in time. We first saw the value 100 for the object, then we saw the value 125 for the same object, but through a different reference, and then we saw the value 100 again. Now this can only happen with multiple pointers like this to the same object, but it can happen, and it's not something people tend to think about. Now previously we saw that we were allowed to do redundant load elimination inside of a loop. For instance, we could realize that our array does not change throughout the entire loop. And we can take all of those logical loads of array and turn them to a single load of array outside of the loop. And that's a great optimization, but that has really nasty implications for concurrency if you actually do want to see the change to a variable. Let me show you. This is also a loop redundant load elimination. While not shared done, you can imagine this being a static variable or an instance variable, however you want to share it. Well, just like the array, we can take that and we can load it into a local variable. And if that value is false, we could loop indefinitely. And this follows very directly from the previous example with the array, but it's usually very surprising to people. Unless we make these variables volatile in these types of situations, then we can have things like time travel, we can have things like unexpected infinite loops. you have to have some sort of synchronizing action, whether it be volatile or synchronized or a lock object. And what about those out of order things? There's no real problem having x equal 2, y equals 3, and flipping their order in this example here. It doesn't change the outcome, not for this one thread. But what if we have out of order and we're sharing a piece of data? If we believed that the previous example was valid and we were allowed to switch the order of x and y, then that means we're also allowed to switch the order of these two statements on the left. Shared data equals something, shared done equals true. So we're trying to set some data and then signal to the other thread that we're done. The consumer is spinning on shared done, which, as we've already seen, could spin indefinitely, so we already have a problem. But we have another problem. If we were to flip those two assignments, which we've seen is valid, then we would set shared done equal to true first. We could come out of the loop, and the shared data would not actually be available yet. Again, making the variables volatile would solve that. It keeps the assignments in the right order and the reads in the right order. But that's not a very good solution. What you should really do in this case is introduce a synchronized block and use wait and notify. But this isn't a talk on concurrency, so we're not going to go into all that detail. I just want you to understand how the compiler complicates things. Basically, the compiler has the leeway to reorder and eliminate whatever it feels like, unless you tell it that there is a synchronizing action or there is some sort of dependence like we've already seen, whether it be a control dependence or a data dependence. In this case, if x greater than 0 has a data dependence on the preceding assignment to x, any assignments to x before that, the compiler could probably get rid of. And then the printx has a control dependence on the evaluation of the conditional. But outside of that, the compiler can kind of do what it wants. And to a certain extent, this is even true in the hardware. Most hardware will reorder memory accesses. ARM will reorder pretty much everything. It'll move loads after loads, loads after stores, stores after stores, and stores after loads, as long as they're not to the same variable. If they're to the same variable, we need to keep them in order. Power does the same thing. Intel will reorder quite a few things. It will move a load after a load. It'll move a load after a store, or a store after a load. But it won't reorder two stores. So the example we saw before still happens on Intel with Java. Wait, what? Why? Because the Java memory model allows the compiler to reorder things. So the compiler can output them in the other order if it feels like. Intel will then keep them in the wrong order. So you have to understand not just your hardware's memory model, you have to understand your language's memory model, and it's the job of the compiler to use the hardware appropriately to achieve that goal. AMD 64 is a little more conservative. It only reorders loads after loads and stores after loads. Basically, it doesn't reorder anything after a store. And Spark has a total store order mode, which is its default. It also has a much looser mode, and it only reorders stores after loads. There are some other aspects of what can be reordered, but this gives you the basic idea. Okay, so the compiler does these types of optimizations all the time, but is there a situation where it can't, other than us marking the variables volatile? There is. For the compiler to know this is okay, it has to know that memory doesn't change between two accesses to p.x, for instance. So there has to be nothing interleaving that could have changed p.x. The way HotSpot tracks this is by introducing this notion of a memory region. So every time the compiler thinks the memory may have been modified in this thread, it is obligated to reload p.x, because we have to show changes in the current thread. We don't have to show changes from other threads. The compiler must always show changes from this thread. If memory doesn't change, well, then we can do load elimination. And it really is just another flavor of global value numbering or common subexpression elimination. It's just, we have a load operation, it takes a memory region, it takes an address. If those two things are the same as a load we've already done, we join them together. So how does the compiler know when memory may have changed? Well, of course, if you assign p.x, that would be a change to memory. But there's another case that's a little more interesting. Let's say you call a function, foo. Foo could have side effects, and the compiler doesn't necessarily know that. So it has to assume that after the call to foo, foo may have had a reference to the point object. It may have changed the value of x, and therefore we have to reload. And this is starting to get at the heart of the problem of what was wrong with our Arraylist example. Why it's not written in the naive way that we think it should be. Because calls can be a challenge for a compiler. Let me show you. Again, we'll use jitwatch's sandbox mode, this time looking at the revisiting redundant loads example. As with the example before, we have a class point with members x and y. and we calculate its distance from the origin in a hot loop. But hot distance looks a little bit different this time. In between the loads of p.x, I have a call to a function that can't be optimized by the compiler. And I do the same thing between the loads to p.y. And because the optimizer can't compile this, it has to pessimistically assume that memory changes. And so it will have to reload p.x the second time and reload p.y the second time. The way I've made it hard to optimize is by nesting a whole bunch of calls. Without having so many calls, the compiler would actually manage to optimize this, and we'll see why a little bit later. But I just want you to see how this works. Let's run it and look at the assembly. Here's the first load of getFieldX, and the compiler has worked really hard to try to get rid of those calls so that it can know that memory didn't change, but it didn't quite succeed. And so we have to reload X again on the other side. And there's the load of Y, and then of course the same thing applies again to the next load of Y. The compiler has to know that memory did not change, and it can only really do that by eliminating the calls entirely. It was not able to do that here, so it had to reload. And you can see how that would be a challenge when you're calling a function object inside of a loop, as we're doing with our Arraylist forEach. Now, if you are watching very closely, you might think, but the problem is that the variables weren't final. Alas, that won't help us either. Let me show you. I will make point.x final and point.y final, and we'll look at the assembly again. And when we look at the assembly, we still see a load of x, we still see a bunch of calls, and we still see a load of x again. Why? Well, unfortunately, the reflection API allows us to change final fields. And the compiler pessimistically assumes you're going to use the reflection API. So even making the field final is no guarantee that the problem won't happen. This time we've scratched the surface of some of the concurrency implications caused by the compiler's optimizations. And I assure you there are more. Writing concurrent code is hard, and you need to understand what the rules are carefully. But that's for another series. For now, we're going to return to focusing on other concepts in the compiler, namely, how does the compiler handle types? This time we're going to examine how the compiler handles types, the final piece of the puzzle we need before we can try to tackle Arraylist forEach in earnest. Earlier we saw an example of constant propagation. This was an optimization that didn't get done by Javac, but does get done by the just-in-time compiler. But what the compiler does isn't actually constant propagation per se. It really actually propagates types, but probably not what you think of as a type. You think of a type as int, but the compiler tracks the type at a far more fundamental level. It thinks of the set of possible values that this variable can take on at this point in time. So at the very beginning, when we set x equal to 10, the type of x is 10. It's a numeric range with a lower bound and an upper bound both set to 10, which happens to turn into a constant. But really, it's viewed as a type that just folds to a single constant. And then we can track this type as it moves from the stack to local variables back to the stack again. And then, of course, we can do the same thing for y. And when we add the two types together, well, we add their lower bound and we add their upper bound and we get a new type, the type 15, and ultimately return the type 15. So we're not really propagating constants, we're propagating types. And this interacts with our Phis and SSA that we saw before. The type of x0 is 10, the type of y0 is 5, the type of x1 is 20, the type of y1 is 10. And from that, we can deduce that x2 is in the range 10 to 20, and y2 is in the range 5 to 10. And this is what HotSpot does. What it actually uses is called a type lattice. I'm not going to explain all the properties of a lattice, but the important thing is it has a center line of constants. So we don't represent constants per se, we represent types. And we can actually construct a lattice for objects as well. And again, the center line is constants. So the string foo, the constant null, or an XML node that we just created can be represented as types. And we can also represent sets with different properties, references that include null and references that don't include null, which allows us to do some cool optimizations. In fact, since we're doing all this reasoning about types, types are really optional. You've probably never really thought about it, but these two pieces of code are equivalent. And yet one only mentions foo once, because there is no local variable, and the other one has to give a type to the local variable. But they do the same thing. Do they compile to the same thing? I certainly hope so. Now don't get me wrong, it is true that these examples will produce different bytecode. Here's the example with the variable, which produces this bytecode. And we can track the variable foo from the stack to local variables and back again. But the same process applies even when the local variable doesn't exist. we have to track the values in the stack slots. We'll know that the first stack slot contains a foo, and then we'll duplicate it and it contains another foo, and then we're going to call the foo constructor, and at the end we'll actually know that we're calling foo's hash code, which turns out to be object hash code. And so we don't even need to do a dynamic dispatch. And this is happening even though there's not a variable. So the ironic thing is, we make you type the type of a variable, but the compiler has to do its own type tracking anyway. It was always doing type inference from the right-hand side. We don't really need you to type the type most of the time. Let's satisfy ourselves that the machine code really does turn out to be the same. As before, we'll use jitwatch's sandbox mode, this time looking at the type propagation example. Here, we are calling a hot method 20,000 times inside of a loop, and at first, we're assigning a variable foo inside of our hot method. To make sure that the hashcode call doesn't get eliminated, along with the construction of foo itself, we're going to store the value of hashcode into a black hole, borrowing an idea from JMH. And if we run this, and we copied its assembly code to the clipboard, we could then run it again after getting rid of the variable and simply constructing an instance of foo inline. And if you run the modified code and copy that to the clipboard as well, you could store them both to files and then compare them in your favorite diff tool. Here I'm just using Eclipse. And we can see a lot of differences, but they turn out to all just be addresses. The actual assembly code is the same, because the compiler doesn't need your types. It has to reason about types anyway. So the final assembly code ends up being the same because the same type deduction is done. It's just sort of a cruel joke that we actually make you type explicit types. We don't really need them, at least not most of the time. And we can do the same type of reasoning about types for objects as well. Imagine we're trying to concatenate together a user's first name and last name. Well, in Java, before you can access a member variable or a field, you first have to prove that the reference isn't null. If it is null, we have to throw a null pointer exception. Does that mean we have to check it every single time? No. We can start with the user object, and we could say the type of our user object is any user object or null. And before we can access user get first name, we will have to do a check to say, is the user null? If so, throw a new null pointer exception. But once that's done, either we've exited the method, or we now know that the user isn't null. And so from that point on, we can say that the user is in the type of all users, and it doesn't include null. And then, when we reach the check that logically comes before get last name, we now know that user isn't null, and we can eliminate the check entirely. This is just another form of dead code elimination based on reasoning about types. That's all it is, but it allows us to remove the overhead of some safety checks. Of course, HotSpot has other clever ways of doing that, as we're about to see. Again, we'll use jitwatch's sandbox mode, this time looking at the null tracking example. It includes a user object. It doesn't have the get first name, get last name methods. Instead, we're just going to access the variables directly, but the concept is the same. Construct a static user variable John, and in a loop, calculate his full name. Let's see what the assembly code looks like. Here is the get field for first name, but I don't see any construction of the null pointer exception. That's correct. HotSpot has a clever trick for how it does this, the details of which we'll discuss a little bit later. But you can see that there is a comment that says there's an implicit exception. So this is actually the checking of the null, and it dispatches to this address, which will actually raise our null pointer exception. And when we come down to last name, we don't see that. There's no implicit exception raising, because we've already proven by this point that the user object is not null. So we don't need to do the exception checking for accessing the last name. And this is all done through type tracking, in the mathematical sense of types, not the Java notion of types. After all, that's actually where the keyword class comes from. And of course, since this type reasoning builds upon SSA and Phi functions, it works for loops too. Now if we look at the canonical for loop, we can say I version 0 is in the type 0. And we know that I version 2 is in the type 1 up to int max. Why int max? Because we know that I1 is in the type 0, our initial value, because it's a merge of I0, which is of type 0, and I2, and int max because we know that arrays can have at most int max elements. So I1 is in 0 to int max, and I2 is in 1 to int max. And this all follows just from reasoning about types. Not quite the notion of types you might have been expecting, but a useful one for the compiler. This time we're going to put all the newfound compiler knowledge to use to try to analyze something real, Arraylist forEach. Here's what we expected Arraylist forEach to look like. And I told you this isn't actually what it looks like. But we're going to try to optimize this so that we can get a better understanding of why it's implemented the way it is. So this canonical example would loop from I, starting at 0, to I less than the size, that's the current size of the array list, incrementing by 1, and having the consumer accept the current element. Let's make our problem ever so slightly simpler by considering an array stream forEach instead. So rather than having a separate size variable, we just always go through the whole array. The extra size variable adds an additional complication that we will address later, but for now, let's just make it slightly simpler. How would we optimize this? Well, one of the major challenges for Java is it adds all these safety checks, which is wonderful for us as developers. We'll get a null pointer exception instead of having a segfault. We won't have security problems because we go out of bounds on arrays, but the runtime has to check these things, one way or another. Fortunately, the compiler can often prove them away. But let's think about what it would actually have to do. First, we'll set I to 0. Before we can even access the element's length, we have to first prove that this element isn't null. If it is null, we have to throw a new null pointer exception. Then we come into the loop body. Before we can access the element, again we have to check that this element isn't null. If it is, we have to throw a new null pointer exception. If I is less than 0, we'd have to throw a new array index out of bounds exception. And if I is greater than or equal to the element's length, we'd have to throw a new array index out of bounds exception. And if the consumer object is null, we have to throw a new null pointer exception. All of these checks are implied. We don't have to write them, but one way or the other, the VM has to do them. Hopefully it can prove most of them away. Let's see how that would work. First off, we can determine the type of I is between 0 and the integer max length. And we can use that to say that if I is less than 0 is never true, and we can get rid of that check. That one's easy because it's a local variable. We can also observe that memory doesn't change up until the point of the call, when we call consumer accept at the end of the loop. So we can load elements once and reuse it for many of these lines. We can see if elements is equal null, throw a new null pointer exception, and we can reuse that for the length check, the elements check again, and the next length check. And of course, this allows us to get rid of a null check because we've now seen that this local variable isn't null, or we've already thrown a null pointer exception. So inside of the loop, we can get rid of the throwing of the null pointer exception. But this only works for one iteration of the loop, because after the call, we have to reload a new value of elements. So we have elements version 0 when we come into the loop, and elements version 1 that merges with that as we go around the loop. So we are reloading every cycle of the loop, and we have to do at least one test each time. Okay, what about the bounds check? Well, we can canonicalize our I greater than or equal to the element's length to not I less than the element's length. And now we have a common subexpression, or really global value numbering, that we can join together with the check as we come into the loop. And that can be eliminated as well, because we wouldn't have entered the loop if we could throw the array index out of bounds exception. So we don't need the check at all. And this is an improvement because we're only checking once per iteration. But unfortunately, we are having to reload elements.length every single time because of the call. Still something else we're having to check every single iteration as well. We're having to check if consumer is null every time through the loop. Is there a way we can get rid of that? There is. We can use a global optimization called loop peeling, where we peel off the first iteration of the loop, or the first n iterations of the loop, hoping that by doing so, we can discover some facts that will hold for the remaining iterations. Namely, consumer isn't null. Here's how it works. First, we load elements into a local variable. We check if it's null. And now we perform the first iteration of the loop. If 0 is less than the element's length, on this first iteration and first iteration only, we check if consumer is equal to null and throw a new null pointer exception. If it is null, we've exited the method. If not, we now know consumer is not null using our type-based reasoning from before. After the call to consumer accept, we have to pessimistically assume that elements may have changed, even if it's final. So we have to reload it, check if it's null. If it is, throw in a null pointer exception. And now inside the loop, we don't have to check if consumer is equal to null every time. We've now proven away all of the checks inside the loop. We don't have to check the nullness of elements. We don't have to check if I is less than 0. We don't have to check if I is greater than or equal to the element's length. And we don't have to check if consumer is null. We have to do some of those things on the first iteration, but most of the time, we get all the safety without any of the checks. That's pretty powerful. But if only we knew that the consumer didn't change memory, then we could take our optimization so much further. We'd only have to load elements once, and we'd only have to load its length once, and it would run that much faster. Typically, the compiler can do this, but in the case of Arraylist forEach, it's quite difficult. So the authors of the JDK, knowing this, did it themselves, because the compiler cannot make that assumption, but the authors of the JDK could. Let me show you. Switch to your IDE and open up the forEach implementation of Arraylist. And here's what you'll actually see. The most obvious difference is the mod count. The collection tracks how many times it's been modified so that it can raise a concurrent modification exception. But that's not what I want you to focus on. What I want you to look at is the fact that it creates a local variable for element data and a local variable for size. Is this legal? It's legal for all the reasons that our optimizations are legal. It's legal as long as we expect that the consumer accept, here called action accept, never changes the array list. That's part of the API rules for Arraylist forEach. But the compiler doesn't know that that's a rule, and it can't know that that's a rule. It can only do the same optimizations if it can prove that action accept doesn't change the array list. If it can't do these optimizations. Since the JDK authors know that this rule applies in this context, but the compiler may not be able to do it, they've done it by hand. They've taken element data and they've stored it into a local variable, and they've taken size and they've stored it into a local variable so that they know it will get optimized. Unfortunately, if we look at older methods, this isn't the case. For instance, index of. It contains a call to object equals. And while I think we'll all agree, your object equals should not change your array list, it could. And unless the compiler knows that it doesn't, it has to pessimistically assume that it will, and it's obliged to let you do it, even though it's a terrible idea. And with that, I hope you now have a sense of the challenge that a call presents to the compiler. In the previous segment, we learned how calls can pose a challenge to the optimizer. Now we're going to learn how it deals with it, through a technique called interprocedural optimization, or more specifically in HotSpot, inlining. But first, let's revisit what the challenges of a call are. We've seen how calls complicate reasoning about memory and force us to reload variables, but calls have other implications too. Calls may raise exceptions, which means they're control flow, and control flow cannot be reordered by the compiler, so that makes it hard to move code around, which the optimizer would like to do. And calls are safe points, at least in HotSpot, which means they can cause the GC to run, and the garbage collector is free to relocate objects. So again, that would force the compiler to reload variables, which it would like to avoid. The solution in HotSpot is a technique called inlining. The idea of inlining is a simple one. We copy and paste the contents of a method into its caller. The naive explanation for why we do this is that because for a small method, which only has a small amount of code, the overhead of manipulating the stack to put the method on and off the stack is disproportionate to the actual code we're running. But that's only part of the reason. It's really to allow us to learn about properties of the method. Does the method not change memory? If so, then we can do redundant load elimination. Or even if it does change memory, if we know it only changes floats, we don't have to worry about changes to ints or objects, and we can take advantage of that. If it's a call, we have to assume that anything could have changed. And we can find out if it doesn't raise exceptions. If it doesn't raise exceptions, then we're free to move things around. And it allows optimizations across the boundaries of the method itself. We can look at the caller and the callee, as it's called, as one big unit and optimize the combination of the two, rather than just optimizing each one in isolation. But the first thing we need to understand when talking about inlining is that there isn't just one type of call in Java. The syntax is always the same for us, but for the VM, the bytecode is different. There are two types of direct calls, invoke static and invoke special. You can probably guess what an invoke static is for. It's for static calls. But what about invoke special? It's for constructors and private calls. And then there are three types of indirect calls, or what in C++ or C# you'd call a virtual call. There's invoke virtual, which is used for references to classes. There's invoke interface, which is used for references to interfaces, and invoke dynamic. Invoke dynamic is the only new bytecode that's ever been added to Java, and you're probably aware of its use for dynamic languages, although it has some role to play with lambdas in Java 8 as well. But we're just going to focus on the top four. Starting with invoke static, and actually a specific flavor of invoke static, one that's calling an intrinsic method, or at least an intrinsic method for C2. Here we have our usual setup, creating a random array of integers and calling a min function 20,000 times inside of a loop. And the min's job, of course, is to find the min of all these values, but it does it by calling mathmin, which you might think is wasteful. Why do a call when we don't need to? It will get inlined, and there will be no difference than if we had written if x less than min, min equals x. And that's it. But how are we going to know if inlining happened? Again, there's a set of flags that you can use to see what's going on inside the VM. So to see that the inlining happened, we're going to run Java with plus print compilation and minus background compilation, as jitwatch does, in addition to plus unlock diagnostic VM options, which we need for our next flag, plus print inlining. And now you can see the VM has printed a tree of inlined methods. So in thread local random next int, it's inlined a method next seed, which was 32 bytes. It's inlined thread current thread, which is an intrinsic, and a couple unsafe methods as well. And down here, what about our min? Well, in our C1 compilation, our tier 3 compilation, intrinsic inlining inlined our min method. And down here in our C2 compilation, it is again inlined our min method, but this time it says it did it because it's an intrinsic. Certain methods are intrinsified at different times, or only in C2 and not in C1. They always do the same thing, it's just a matter of how the JIT handles them. C2 has special knowledge of min, and so it will run fast no matter what. Turns out, C1 not intrinsifying min doesn't affect the performance. It's just you get the same code whether you use the Java code or if you had intrinsified it in C1, so it's not intrinsified by C1. That's not quite so true for C2. Now let's use jitwatch's sandbox mode to verify that there really is no call in the assembly code. Select our min function, and here we can see that it is an invoke static. And if we click that, we can find the corresponding assembly code. But there's no call here. The min is done by these two instructions, a compare of R10D and R13D, which contain x and min, and then a conditional move to move whichever value is the lesser of the two. And that's it. There is no call. The min function is free. You're actually well advised to write small functions and just let the compiler get rid of them. It's actually very good at it. And of course, being good at it means it must also be able to get rid of calls to Java methods as well, not just intrinsics. Now let's see that this can happen for Java methods too. Here we have an example with a loop calling sum of squares, and sum of squares in turn calls a square function, which is of course small. It just contains x times x. And both of these methods are static. So these should be invoke static calls to Java methods. Let's run it and see if this gets inlined. Let's look at sum of squares. Again, it is an invoke static call. And where is our multiply? It's right there, an imul of EAX. This is our call to square. There is actually no call overhead. Writing little functions does work, and it does perform well. There's one last easy case for the compiler. Invoke special calls. These are also direct calls to things like constructors. To illustrate, we have a loop calling a factory method 20,000 times, and the factory method is simply calling new object. And if we look at the JIT code for the factory method, we will see that this invoke special call, well, it's nowhere whatsoever. Here's our new. That's a call, but there is actually no call to the constructor because we've inlined object init, and object init happens to be empty, so there's no machine code whatsoever. This is the most extreme case of an easy method that would have high call overhead, and the compiler does get rid of it. In fact, the compiler is very good at getting rid of calls to small methods. It will get rid of calls to methods with less than 6 bytecodes, no matter how hot they are. This is the max trivial size. Unfortunately, 6 bytes is not a lot of bytecode. It's enough for a setter. It's also enough for a getter. But the compiler will go further. It'll get rid of calls to methods that are less than 35 bytes if they're called at least 250 times. These are the max inline size and the min inlining threshold. That's not a lot of bytecode. It's enough for a moderately interesting loop, but that's about it. Fortunately, the max inline size is poorly named. It's not actually the max. The max is the frequent inline size, 325 bytes. And this will get inlined if the method is hot, that it's called at least 10,000 times. And 325 bytes is quite a bit of bytecode. And the compiler will do this up to 9 levels deep and 1 level of recursion. I've actually seen places where the compiler has inlined as many as 250 methods into a single compilation. So you don't need to create big methods yourself. You can let the compiler copy and paste the code to create large methods and optimize them well. By writing small methods, you give it interesting ways to compose things, and you make your code more maintainable. To let you know if you've managed to do this, jitwatch actually comes with an extra tool called jar scan, which will scan your jars and tell you if you have methods over these different sizes. But I'll let you play with that on your own. Now we've seen how the VM gets rid of calls, at least the easy ones, the direct ones, static and virtual calls. What about the indirect ones? Well, we're going to come back to that a bit later. This time we're going to take our now nearly complete understanding of high-level compiler optimizations and revisit some of the performance mysteries from before. starting with one of our earliest examples, where we were measuring the performance of object allocation inside of a loop, in chunks of 1,000. As you may recall, the numbers we got at the end were almost unbelievably good. 0 or 1,000 nanoseconds on Java 7, and around 70 or 80 nanoseconds on Java 8. How could we possibly allocate 1,000 objects that quickly? It's easy, by not allocating objects. We've learned that we can inline constructors, and we've learned that the object constructor is empty. So that means the first thing that the compiler can do is get rid of the call to object init altogether. And that leaves it with a single assignment of a piece of memory that's never used anymore. Well, that's just a dead store, so we can get rid of that as well. And since the loop is then empty, we can then eliminate the loop. And so we're measuring what? Just the call from system nanotime to the next call to system nanotime. And surprise, surprise, that's very fast. Sometimes it's so fast on Java 7 that the clock hasn't even ticked forward, so we get a 0 difference. Other times it has ticked forward, and we get a 1,000 nanosecond difference, because that's the quantum. Is this really what's happening? Well, let's find out using jitwatch. We can load our simple program from before in jitwatch's sandbox mode, and now we can run it. And we can find the OSR of main, and we can see the assembly that was generated. Here's our new and our invoke special. Let's click on them. They're nowhere to be found in the assembly code. What we can find, the invoke static call for system nanotime, the first one, and the second one. Now there is some stuff in between, but nothing that's allocating objects, and that's why it runs so fast. The quickest way to allocate objects is not to allocate objects, and that's what the VM does. Okay, but why doesn't HotSpot always inline when we expect it to? Why did it not inline when we were doing our redundant loads with a call in between, as we did in our revisiting redundant loads example? Why didn't inline can't optimize? Well, it did. It just couldn't inline all the way. As you can see, if we go look at our hot distance method, it actually tried really hard. Here's our invoke static call, and it inlined can't optimize all the way through F8. The problem is, it only inlines 9 levels deep, and F9 is just one step too far. If we had something more sane, then it should actually be able to do it, as in this inlining and redundant loads example. It's almost the same, but this time, call is just a simple empty method. And we could put some stuff in it too, but with only a single level of call, or even 9 levels of call, we should actually still be able to do the redundant load elimination. Here's an invoke static call, and we can see it's nowhere to be found because it's an empty method, and the compiler's just gotten rid of it. And if we look, there really is just one load of getFilledX and one load of Y. We only need to do the single load because we've proven that we don't need the call, and if there's no call, we don't have to worry about memory changing. And now the optimization can happen. Is that really it? Let's test the theory a little more. You can actually configure your sandbox to disable inlining. And then if we run, we should see the optimization go away. Now, jitwatch is highlighting our invoke static calls in red because they didn't get inlined, and it's concerned about that because it's going to affect our performance. Now we have to load X once, and we have to load X again. It really is the call that gets in the way, and that's why inlining is so important. But if that's the case, how do we make sense of our weird results from our JMH example from a while ago, where we put the black hole consume inside of the loop? Well, let's test it. Let's use the example inlining and loop invariant. It's very similar to the example before, but this time, rather than calling black hole consume, I call my own consume method, which, as you're probably expecting, is just an empty method. And let's run this and see how it performs. Wow, it's running really fast. Why is that? Well, we're using an empty method, which means it's an empty loop, which means basically we're doing a no-op. Remember, the black hole consume is designed to prevent this sort of optimization so that we can write a meaningful benchmark. It's deliberately hard for the VM to optimize it, which unfortunately is sort of what you end up with when you can't inline a method. And JMH gives us a way to demonstrate that, which I'll show you in a moment. JMH is finished running, and we can see that all 4 approaches, the C-style loop, the manually hoisted loop where we assign length to a local variable, the enhanced for loop, and one I've called almost fully hoisted, run at the same speed. They all get the same set of optimizations because we can see through the method and do everything. And what happens without inlining? We can use the JMH annotation compiler control with a mode of don't inline to set the consume method to not be inlined by the VM. Rebuild our benchmark, and we'll have our results. Right away, we can see that things are taking longer to run because without getting rid of the call, the VM can't get rid of the loop either. And so now we really do have to iterate over the results to get the answer, even though there isn't one. And our benchmarks are now running at different speeds. Some of them are more optimized than others. Will they have similar performance characteristics as the black hole consume from before? It turns out they will. And once this is done running, we're going to go look at the source code and see if we can understand why. As with the example with black hole consume before, the hoisted version is the slowest. That is, the one where we create a local length variable to hold the length of the array. The C-style one came in second, and the enhanced version and the almost fully hoisted version tied for first. Now let's think about what the compiler actually has to do for each of these. Since consume isn't inlined, the compiler has to assume that this values may have changed. So we have to reload values after each consume call. And we have to do our safety checks. Eliminating the low side check is easy, but the high side check is a little harder. We have to check, is I greater than or equal to this values.length? If so, throw a new array index out of bounds exception. But in the C-style case, we know that we've checked this values length once already when we entered the loop, and it doesn't change until after the call. So we don't have to do the second check. And not being able to eliminate that is actually the problem with the hoisted version. Because we took this values.length and cached it into a local variable at the very beginning, it doesn't have a relationship to this values.length inside the loop. Because after the consume call, we have to assume that this values could be something completely different. And so they're no longer a common expression. So we have to check first against I less than len, and then we have to check separately that I is not greater than or equal to this values.length. And that's why the hoisted version runs slower. And it's not that this is a bad optimization. It just has to be done carefully, and it's actually best left to the compiler to decide when it's a good idea to do it and when it's not. But what of the enhanced version? Doesn't it just amount to the code above? No, it doesn't. It actually compiles into this, the almost fully hoisted version. All we really need to do is put values into a local variable, like we saw Arraylist forEach do. And now we can optimize, even if consume doesn't get inlined. That's really the trick. As it turns out, the enhanced version would also create a local variable for the length as well, but that's entirely optional. The important part is that there's a local variable for the array. And if you put all these things together, we can come to some rather surprising conclusions. You might think that the enhanced for loop over a list is a bad idea, because it calls list iterator, and then we have to call iter has next, and then iter next. But this actually performs very well. We can inline iterator, and the constructor inside of it, and iter has next, and iter next. After we've done all that, we can actually just get rid of the iterator object altogether. It never leaves this stack frame. This is the true meaning of escape analysis. Not that we can dead code eliminate one silly object like we did in our early example, but that we can put an actual object on the stack because we never actually share it. So all of its member variables become local variables. And that's very powerful for optimization. With everything local, we now know that memory doesn't change. And those member variables, they actually capture some of the values of the list itself, like its size, so that that's effectively already pulled out of the loop. And this is very powerful. The iterator is almost always faster, which is probably not what you expected. We've seen how the VM can statically optimize your code, or indeed how any compiler could optimize your code, be it a C or C++ compiler, a Java compiler, or even a JavaScript engine. But the real magic of managed runtimes, and the JVM in particular, are speculative optimizations. But speculative optimizations come with some peril. To make them work, we also have to be able to de-optimize. The VM needs to be able to speculate that something that was true will remain true, and have a backup strategy if it turns out to be wrong. And that backup strategy is de-optimization. You've actually already seen an example of it, the way null pointer exceptions are handled. If you'll recall earlier, we saw this mysterious piece of assembly code, and it didn't say compare this value to null. No, it just said implicit exception dispatches to this address. What was that all about? What that was about was the VM assuming that you don't just go and create null pointer exceptions all over the place. That most of the references it will access will indeed not be null. Or at least you'll have an explicit null check beforehand. So you don't just create null pointer exceptions. Is there a way the VM could optimize that? There is. It uses something called implicit null checks. The idea is simple. Let's make handling null more expensive if it allows us to make handling non-null less expensive. How would we do that? Well, the hardware already has handling for null. It's called a segmentation violation, and that's actually what the compiler does. It intentionally creates situations that will cause segmentation violations. But the magic of a managed environment is the VM can install a signal handler to handle segvs. So what actually happens is we dereference the value. If that turned out to be a null, a segmentation violation occurs that calls the signal handler, and the signal handler says, oops, I meant throw a null pointer exception. And this prevents us from having to do a branch inside the assembly code, because branches are expensive, particularly on non-x86 hardware. The memory subsystem already has handling for nulls, so we just take advantage of it. But this does have a downside. Trapping in hardware and then through the OS is slow, and if we end up doing this very often, it's not a good idea. So the VM has a way to reverse this decision. Let me show you. I have an implicit null example that calls a hot method 20,000 times inside of a loop. First with the string foo, and the hot method's just returning the object's hash code. And then we sleep for 5 seconds to let the compiler kick in, and then I assert that I'm tempting fate by calling it with null. Let's see what happens. We're going to run the example with print compilation. And to make the output a little easier to read, since I'm using Java 8, I'm going to use minus tiered compilation, because it's not necessary for this example. And we can see that the hot method gets compiled. That's expected. But then when it starts to tempt fate, the first time it doesn't do anything. And then the second time it doesn't do anything. But on the third time, it makes the method not entrant. Now we saw this before with tiered compilation. When a new tier became available, it retired the old one. But I ran without tiered compilation. What's happening here? The compiler ran under the assumption that nulls were not going to happen regularly when we're calling hash code. But now they are happening, and once it sees 3 of them, it says, that's enough. I'm going to resort to a different strategy. What I was doing isn't working. It's too slow if nulls are a thing. When we assumed that nulls were not an issue, trapping was fine. But now, it would be better to go and put in an explicit check. But it hasn't even done that yet. It's just made the method not entrant, which means all the callers are going back to the interpreter. Now don't get me wrong, given long enough, the VM will go back to the interpreter and it will eventually compile with C2. Let's see if we can make that happen too. We'll do that by simply cloning the top of our program to let the hot method get hot again. And now we'll run it one more time. And hot method does get recompiled. The power of this technique is that we can speculate something, and if it turns out to be wrong, we can correct the mistake and we can try a better method. A C or C++ compiler, they have to be pessimistic. They have to assume that all things are possible, and they can't make any assumptions based on what's presently happening. HotSpot can. In fact, HotSpot will even go so far as to optimize for nulls being common. Here I have a program, hotNull, with a main method that creates arrays of random objects. And it has some count methods that count the frequencies of null pointer exceptions. And each of these methods is separate so that they'll be JITted separate. We remove all the possibility of optimization changing our results. Each identical count method will be JITted separately. And we get a results object, and the results object doesn't just consist of how many null pointer exceptions we catch inside these count methods. It also counts how many unique objects we got, because the count methods look like this. We get the number caught, and we count that inside the catch block. But we also add the null pointer exceptions to a set, and then we return the size of the set. You'd expect those two numbers to be the same, but of course they're not. So what do we get? Let's run it and find out. When 10% of our 100,000 objects are null, we catch 9,836 null pointer exceptions. But slightly fewer, 9,779 objects are in the set. When 50% are null, 50,149 were caught, but far fewer, 21,576 items are in the set. 90%, 89,981 caught, only 37,719 exceptions in the set. What's going on here? Well, the VM has realized that I'm creating a lot of null pointer exceptions, and it's decided to optimize that for me by rethrowing the same null pointer exception over and over and over again. But it's not doing that because construction is expensive. Well, at least not because new is expensive. Allocating an object's really fast. On my laptop, it takes about 6 nanoseconds. No, it's doing it because filling in the stack trace is slow. But if we're going to share the null pointer exception for multiple different call sites, well, our stack trace would be wrong anyway. So it just doesn't fill it in at all. Up here, these are the printed out stack traces of all the duplicate exceptions for the 10% case. You don't get to have one. So nicely enough, the VM has optimized my hot exception, and now it stubbornly refuses to tell me where it is. We've started to scratch the surface by seeing how the VM handles nulls. But not all DOPs are handled the same way. And next time we'll learn about a technique called uncommon traps. Last time we started looking into the world of HotSpot speculative optimizations by looking at how the VM handles nulls. This time we'll dig deeper and look at something called uncommon traps. HotSpot doesn't just speculate about null checks, it speculates about all sorts of things. Type checks, array type checks, range checks, and it has to deal with some weird cases, like classes that haven't yet been loaded, or classes that haven't been initialized. And it deals with many of these things through something called an uncommon trap. Let's take a look at an example. Here we have a class called unreached. As usual, it calls a hot method 20,000 times inside of a loop. But the hot method uses the result of a static variable object, and it sets a single output variable to false if the object is null, or true if the object is non-null. As you can see before the first loop, object is null. And the VM is going to speculate, because the object was null, that it always will be null. But it's not going to stay that way. After the first sleep, we change the object to non-null and print out a message. Then we let the method get hot again. And then we sleep again, and then we revert it back to null one more time. These changes back and forth are what VM people would call phase changes. The application was doing one thing, and now it's doing something else. Let's see what happens as the phases change. As we've done before, we'll run with -xx:"print compilation and -xx minus tiered compilation if you're using Java 8. And we can see that our hot method gets compiled. And then when it switches to non-null, the method gets made not entrant. And it compiles again, seemingly immediately. And then when it goes back to null, it doesn't get made not entrant again. What's happened here? The VM has effectively eliminated the else branch the first time the method was compiled. That doesn't mean it got rid of the check. It had to do the check to know if it made a mistake. But it can only do the else branch. If that's true, we're good. Else, it does an uncommon trap. And when it does an uncommon trap, it bails to the interpreter, because it just didn't generate the code for the else block at all. Let's go one level deeper and use jitwatch's sandbox mode to verify that the code for the else block really did not get generated. This time using a very similar example called unreached phase 1. This part only does the first loop. The hot method is also slightly different. Instead of setting the same variable, down one path we set isNull to true, and down the other path we set not null to true. This will make it a little easier to figure out what's going on in the assembly code. We can click the put static for isNull equals true, and we can find the code for that, but we can't find the code for the not null equals true, because that case just hasn't happened, and it didn't get compiled. Instead, what you'll find is these strange calls. These are calls to the uncommon trap handler. These are what cause us to bail to the interpreter. Now it's important to understand, when the uncommon trap occurs, it's only the current thread that's bailing to the interpreter. The other threads, if they're already running the C2 version, they can run along merrily, as long as they don't hit the same trap. But in this case, where the method was made not entrant, new callers can't come in, so they're also going to get bounced back to the interpreter. So this can have a fairly large impact. In fact, it can have an even bigger impact than you might have expected. Because it's important to remember, we're bailing a compiled piece of code, and compiled pieces of code may have inlined many methods, up to 9 levels deep. And so we may not be bailing just a single method. We may be bailing 3, 4, 5 methods. And when we do this, we're basically doing an on-stack replacement in reverse. We're going from compiled code to interpreted code mid-execution. And it's actually this particular trap that explains the behavior of our less simple program from earlier, where we saw the performance drop off at the beginning of our allocation loop because we had a variable that we changed to non-null. But if you were paying really close attention, you might have been wondering, is this example just silly? Well, yes, it is. But maybe more specifically you were wondering, why did I use an if-else? Or I could have just done this. Would that make a difference? Would replacing it with a not equals change the outcome? Sadly, no. The bytecode is roughly the same, and if we run this, we're going to see the same behavior. So we'll run the program again, just to see. An unreached hot method gets compiled, but it still gets made not entrant, because the bytecode is still an if. And this optimization, if it were an optimization, is done very early by the compiler, without considering profitability. It just assumes that if it can get rid of a branch, it's probably a good idea, but it isn't always. So why do we bother with such a seemingly silly optimization? It doesn't even get rid of the branch. We have to keep the branch to know that we've made a mistake to use the trap. Yes, but optimization isn't just one thing. Consider the example here. X equals 20, y equals 25. Down one branch, the hot one, y equals 15. Down the other branch, the cold one, y equals negative 20, and then we have a diamond with y times equals 2. If we know the right branch is always cold, and we can replace it with the trap, well, we could turn the left branch into just y equals 30. But that saves us just one multiply. That's not all that much. But if after this block there was a test, is y greater than 0? We can now say unconditionally, yes, y is greater than 0, which we could not do if we had to consider the branch on the right. And this is the power of it. While one particular case I may choose may be silly, and there may be no profit there, that doesn't mean there's never profitability. In fact, this optimization can yield about 10%. You just need the right benchmark. Let's look at something else we can do with uncommon trap. Remember before when we were discussing Arraylist forEach, and we decided to ignore the I less than size component? There's a reason for that. It's hard to prove that there's a relationship between this.size and this.element's length. But what if we didn't need to prove it, or at least not statically? Instead, the compiler can prove it dynamically by baking in an extra piece of code that says if the size is greater than the element's length, issue an uncommon trap because of a predicate. This has the downside of sending the entire loop back to the interpreter, but this doesn't happen very often. And this lets us get rid of the bounds check inside the loop, always. Previously, we've looked at some of the speculative optimizations that can be performed by HotSpot. Now we'll look at the most important one, de-virtualization. If you think back to our Arraylist forEach example, we've gotten pretty far now. We've managed to eliminate most of the null checks and most of the bounds checks. But we could do better if only we could get rid of this call to consumer accept in the loop at the bottom. Is that possible? It's an indirect call. It could be anything. It's an interface. We could have 1,000 different implementations. How could we possibly get rid of the call to consumer accept? The simplest approach is something called static de-virtualization, which means we just use our type-based reasoning to figure out that there's only one type at our call site. For instance, here we have a main that sets up a consumer that's just a no-op consumer, and they're declared above. And the consumer and a number are passed to our consume method. Now within the consume method, we don't know the type of the consumer. But if we looked at main as a bigger unit, then we do know the type. We know it's a no-op consumer. We can infer from the right-hand side that the consumer we're using is always a no-op consumer, and then we could follow that value into our call to the consume method, assuming we inlined it, and then we actually know the value inside of consume. Would that work? Yes, it does, but let's verify. We'll run our program with print compilation, and to make the output a little easier to read, since we're going to print the inlining, we'll use minus background compilation. Since I'm using Java 8, I'm going to use minus tiered compilation, so we have a little less to look at. And to print the inlining, unlock diagnostic VM options with print inlining. And there we go. Let's find our compilation of main. Here it is. And you can see it's inlined a few things. First, it's inlined integer value of, and the integer constructor and the number constructor. But those are all static calls, so we'd expect that. But it's also inlined static de-virtualization consume, which is itself also a static call. But just below that, you can see it's also inlined static de-virtualization no-op consumer apply. And it's done this because it realizes that the only value within main, because we're looking at a bigger unit, is the no-op consumer. But how did it manage to inline it up here in static de-virtualization consume? How does it know that we're only using a no-op consumer when it's compiling the whole consume method? I could pass consume any type of consumer. And this is where the real magic starts. The VM uses a technique called class hierarchy analysis, or CHA, that takes advantage of the fact that in HotSpot, classes are lazy loaded. So despite the fact that I may have a function class, if I've only loaded square right now, then that must be the one I'm calling. That or I have a null and we're raising a null pointer exception, and we know how that gets handled. And it uses this information to always inline square apply as long as there are no other possibilities. Let's see this. In the CHA de-virtualization example, we have the class hierarchy described before, but locally I'm just using a square. In fact, I've even typed the variable as a square. And I call 8 different apply functions. You can imagine that these are scattered all over your program, but it's easier to just have them in one place. And they all are pretty boring. They're just wrappers around the function apply. And of course, we call them 20,000 times inside of a loop, and we sleep for 5 seconds. Let's see what the inlining looks like for this. Using all the same flags as before, we'll run the CHA de-virtualization example. And we can see, not only in main did square apply get inlined over and over again, but in all the individual compilations of the apply methods, square apply was inlined over and over again. Pretty neat. But this magic doesn't come without its consequences. Let's look at a snippet of this, the CHA snippet, in jitwatch's sandbox mode. Again, we have a main method instantiating a square class that extends a function class. And now we're going to look at the assembly code that's produced for apply 0 and apply 1. Here's our multiply, which looks a little different than what you're used to because this is a double rather than an integer. But there's actually no type check anywhere before this. We don't see an uncommon trap. We don't see one of those strange looking calls before the multiply. So how does the VM know if this is wrong? How does it correct its mistake? We can't use a signal handler and we don't have an uncommon trap. So what's the solution? The solution is for the VM to correct its mistake when a new class is loaded. As soon as another function becomes a possibility, the VM has to correct it, even if it never gets used. To illustrate, we'll uncomment this line that causes the square root class to be loaded, and we'll run our example again. As before, we're going to run with print compilation and minus tiered compilation, but we've already seen the inlining. Let's look at something else. We'll use print SafePoint statistics again, which shows us other types of stop-the-world pauses. Let's see what happens. All 8 of our apply methods get compiled, and main gets compiled as well. But then all 8 methods get made not entrant at the same instant. Without a check inside of each apply method, we don't know when an apply method encounters another type. So they all must be killed, and they must all be killed at a stop-the-world pause, because they won't be able to realize that they've done something wrong. And we can see that this happens because there's this de-optimize line that's telling us the VM had to stop the world to de-optimize those 8 methods. And having a stop the world pause, other than garbage collection, may already seem pretty bad to you. But the consequences are even bigger than you might imagine. In this case, the method's not only made not entrant, it's completely wiped. It's turned into nothing but no ops. And the reason for that is even when returning into the method, we could make a mistake. And so by wiping it with no ops, we slide down into the bottom of the method where there's a deopt handler. And this causes all returning calls to bail to the interpreter too, not just new calls. And remember, this is across n methods. So this could have a pretty large impact. Fortunately, these usually get sorted out very early in the run, and then they don't happen again. But it does contribute to volatility at startup. Now you may wonder, why do we even bother with this? Well, virtual calls in Java are very important. Object equals is a virtual call. Object toString is a virtual call. All sorts of things are virtual calls. And if you're using functional programming in Java 8, that's a virtual call. We use them all the time, and so they need to perform well. Fortunately, most call sites really actually only use a single type. And so if we can take advantage of that, we can reclaim all the speed that we've lost. So do we actually manage to do that? Do we manage to reclaim all the speed? Alas, at least for our Arraylist forEach example, the answer is not quite. Here we have a JMH benchmark, de-virtualization, with a consumer class and our no-op consumer. What we'd really like to see here is for the VM to realize that our no-op consumer is, well, a no-op. And just dead code eliminate all of our loops, no matter whether they're C-style, hoisted, enhanced, or the almost fully hoisted from before. But that's not what we're going to see. It doesn't quite get that far. How does it do? Well, if you were to run it, you'd get output that looks something like this. The enhanced and the almost fully hoisted, they still win. They're still in a tie. But the hoisted and the C style, they're coming out roughly the same. In fact, the C style is a little slower. So we've closed the gap some, but we didn't do complete dead code elimination, but that was always kind of silly anyway. Alas, there is no easy answer to optimization. It's a whole bunch of little things put together, and sometimes different combinations give you surprising results. If you were watching carefully as I scrolled through the benchmark code, you might have noticed I did this no-op consumer apply. Wouldn't it be better to hoist the consumer outside of the loop and make it a local variable? After all, we know it's loop invariant. I'd encourage you to try it. I assure you the results are surprising. So we've started to get a feel for de-virtualization, but that class hierarchy analysis I talked about, it turns out it's class hierarchy analysis. It doesn't work when we're using an interface. And we have to ask ourselves, what happens if we use even more types? We've seen what happens with one type, where we can inline with no guard, and then invalidate because of class loading, but is that the end of the story? Does it only work for a single type? No. We have a solution for interfaces, and we have a solution for two types. And we'll see those next time when we look at type profiles. Last time we talked about a couple ways that the VM can get rid of virtual calls, either through static type reasoning or through a technique called class hierarchy analysis. But I also mentioned that class hierarchy analysis is only for classes, not for interfaces. But de-virtualization is so important, the VM has many ways to do it, including a way that works for interfaces and more than one type. To see how this works, we'll look at an interface de-virtualization example, which at first glance is very similar to our CHA de-virtualization example. The main difference? We're using an ifunc rather than a func. And as you might expect, ifunc is an interface. And all of the apply methods have been modified to take ifunc rather than func as well. But everything else is the same. We use a square, we call all 8 apply functions 20,000 times inside of a hot loop. And then we see what happens when we load square root. We'll run this example to see what does happen. And as before, we're going to print the compilation and the inlining. And here are our results. We can see that all 8 apply functions did inline function square apply. But there's an extra line here that we didn't see before. It says type profile, 6700 of 6700 counts function square. What that's saying is the VM was keeping track of what types we used inside of apply 0. And 6700 out of 6700 times, it was a square. So let's inline that. And of course, the story is the same for all the other apply methods too. And main still gets to inline because of static type reasoning. But then we load the square root class, and we don't see the big deopt pause. We don't see all 8 apply methods get made not entrant at the same time. Instead, we see a couple apply methods get made not entrant, and then they get recompiled, and then a couple more get made non entrant. Why is that? To find out, we're again going to use jitwatch's sandbox mode, and we're going to look at the interface de-virtualization snippet. This is a small chunk of the program we've just seen, just the part using square, so we can see what the first compilation of apply 0 and apply 1 turns out to be. And immediately we can see by looking at the bytecode, this is now an invoke interface call, because we were using an interface, ifunc. And here's our call, the vmols sd. That's our multiply. But there's also this funny stuff before. There's a comparison of what jitwatch says is metadata. And then there's a jump. What is that about? This is a test that our object really is a square. And if it's not, we're going to jump to this label. Let's find the label. Here it is. And this call Q here is an uncommon trap. So we bail to the interpreter if the type is not what we expect. This is a technique called guarded inlining. Unlike in the CHA case, where there was no check in the assembly code, here we have a type check to make sure that the object is a square, and if so, we can still use the inline code. Else, we do an uncommon trap of type class check. But why do we do this? Couldn't we just call function apply down the else block? We could, but if we did that, it would still be a blind call. And a blind call means we have to give up optimizations. So instead, we treat it as an exceptional case. Either it was a square, and we get to do all the optimization, or it wasn't, and we let the interpreter deal with it. And this is a very powerful technique. It allows us to optimize in situations where a C or C++ compiler never could. It just comes with the downside of falling back to the interpreter. But fortunately, this is an uncommon trap. This doesn't require a stop-the-world pause. It just requires this one thread to bail to the interpreter, and then yes, we will lock out access to the method, so new callers will have to bail to the interpreter too, but it isn't a stop the world pause. However, it does come with the extra overhead of the type check, and that does mean that interface calls are sometimes ever so slightly slower than calls on a class. Now that we understand how interface calls are devirtualized, let's go back and take a second look at the source for our interface devirtualization example and see if we can figure out why those methods were made non-entrant. It wasn't the loading of the square root. We don't use class hierarchy analysis. It was actually the fact that after that, function was set to square root, and then we started calling apply 0 and apply 1 again. That's another type. That hits the uncommon trap. But the trap is for each method in isolation. The other 6 methods that we're not using, apply 2 through apply 7, they're fine. They don't need to be made not entrant. They haven't seen square root yet. It's only when methods 2 and 3 see square root themselves later on that they have to be made not entrant. Again, this is because the uncommon trap operates on a method-by-method basis. We're not doing this at class load time. Each method can independently detect its mistake because it has a check inside of it. It's only when there's no check inside that they have to all be de-optimized at a stop the world pause. And we can actually apply this type profile technique to classes as well after CHA has failed us. Here we have a similar example to the CHA devirtualization example before called revisiting class devirtualization. As before, we call 8 apply methods, first with a square, and then we load the square root class, which is going to cause a stop the world de-optimization. Then, as in the interface example, we continue using other types. First we use another square, and we see what happens. Then we use yet another square, and we see what happens. And then finally, we use one more square, and see what happens. We'll run this program with print compilation, and we'll print out the inlining as well, and see what we get. We can see in the beginning, just as before, square apply gets inlined into all of our apply methods. And of course, main still gets to inline based on static type reasoning. And then all 8 methods de-optimize at a stop the world pause because we've broken our CHA assumption. But after that, when we start using another square, square apply is still being inlined. And it's being inlined again? Yes. Another square actually extends square, but the way the type checks are done, each type is handled separately. So our type profile shows us a count of 11,699, of which 4,998 are another square, and 6,701 are square. And that's true for both apply 0 and apply 1, else they're doing an uncommon trap. So when another type, yet another square, is introduced, both apply 0 and apply 1 are made non-entrant, this time not because of a class check, but what's called a bimorphic check. And it's called bimorphic because before we were inlining 2 types, and we've failed to match either of those 2 types. And now we recompile again, this time without inlining. The VM's given up. It'll only handle up to 2 types. After that, the call site's said to be megamorphic, and there's just nothing more the VM's going to do. We're stuck with the call, and we're stuck with the loss of optimization. And so when we introduce yet one more type, one more square, nothing happens. There's no more making not entrant. We're back to just doing a plain old vcall, and that's it. But you can see the VM works really hard to get rid of these virtual calls. It first did this class hierarchy analysis, and then it inlined one type with a check, and then it inlined a second type with a check. So that means this call site de-optimized 3 times. It really wants to do this, if at all possible. In fact, the VM wants to do de-virtualization so badly, it has yet one more method for performing it, called unique concrete method, but we'll talk about that next time. Last time, we continued our investigation into de-virtualization by looking at type profiles. This time, we're going to look at the last flavor of de-virtualization, something called unique concrete methods. As you may recall, with our final example, we came to a rather curious result. Square apply was inlined twice, once for square and once for another square. Now, if you haven't figured it out already, another square, yet another square, and one more square, well, they all just extend square. And they don't override the apply method. So in all 4 cases, we were calling the same method. Why couldn't the VM do better? Well, if you were paying very close attention, you would have noticed when I wrote the inline guard example, I wrote it as funcGetClass exactly equals square. But why would we do that? Why would we make it an exact type check? This looks longer. Yes, it looks longer in Java code, but it's not longer in assembly. This is actually order 1, whereas the instance of check, which is probably what you were expecting, is actually order in. And so we use the exact type check, despite the fact that it will reject certain things, like yet another square, and one more square, that should otherwise match. But is there a way to deal with all four classes? There is. This time we're going to look at an example called unique method de-virtualization, which is almost exactly the same as our revisiting class de-virtualization example from before, but with one key difference. This time the loading of square root is commented out. Is that really going to make a difference? Let's find out by running with the usual flags to print compilation and print inlining. And we can see that square apply does indeed get inlined into each of our apply functions, just as before. And of course, main still gets to inline, but now when we use another square, there is no de-optimization. And of course, there is no stop the world pause, because we didn't load square root. And then we can load yet another square, and there's still no de-optimization. Still no methods made not entrant. And one more square, still no methods made not entrant. But what's this at the bottom? Well, there was actually one more change to the file. At the very end of main, I did actually load square root, and this violated our unique concrete method assumption. Up until that point, the VM was able to say, there's only one apply method in the entire function hierarchy, so that must be the one we're calling. But as soon as I loaded square root, that stopped being the case. So this method of de-virtualization can work, and it would actually work if our type had been square and not function. But it only works for function until square root is loaded. As long as we have two implementations, it's no longer a unique concrete method. And with that, you can see that all these different methods of de-virtualization, they're powerful, but they have really non-obvious and complicated interactions. But that is, of course, why the VM has so many of them. Each one may or may not succeed on its own, but you put them all together, and there's a good chance of success. But if that's true, what are we to make of Arraylist forEach? Why does it go to all this trouble of storing variables into locals? The problem is the very nature of Arraylist forEach. It's going to take many different consumer objects. And if it takes many different consumer objects, all of these different strategies, CHA, type profiles, unique concrete methods, they're all likely to break down. And the call site's going to become megamorphic. And if the call site becomes megamorphic and we can't inline it, then we'd give up all optimization. Now, this isn't necessarily something I want you to worry about all the time, but I hope it's something you at least now have a better appreciation for. So what have we learned in this series? Well, we've learned that micro-optimizations, honestly, they usually don't help. If it's something small that could be done mechanically, the compiler probably already knows how to do it, and it probably does it in a better way than you could, and it does it everywhere. However, there are things it can't do, like switching between using heap variables and local variables. Sometimes it can pull that off, but it can't do that if memory changes. So adding local variables can actually be helpful, contrary to what a lot of people would think, which is that they should remove them. And a lot of things that you'd think are expensive, because they're common in Java, we put the effort into making them fast. So dynamic calls, locking, allocation, and garbage collection actually aren't that expensive at all. And because of the complexity, you really have to benchmark carefully before you can draw any conclusions. How many types you use, whether or not a branch is taken or not. All these things can change how the code runs. You have to make sure you created the conditions that are actually realistic. If you try to write a micro-mitchbark and you only use one type, even though your hierarchy contains many types, you're not actually testing what you think you're testing. And the other thing is, optimizations change. Remember that unreached optimization I told you about? Well, I showed you an example with a pointer comparison. And that actually turns out to be the only time the VM does that optimization. But it used to do it at other times as well. It used to do it for integers, doubles, indeed all comparisons, even the evaluating of a Boolean. But that changed, and it may well change back. So you can't just make a judgment and call it done. I've tried to focus on the reasoning that's going to be timeless. But even so, there are other things we do have to consider. Things that are outside the compiler. So before we conclude, we're going to look at a few other surprises. Last time we concluded our look into the dynamic optimizations done by the compiler, although that wasn't all of them. This time, we're going to look at a few other surprises. Things that go beyond the VM. When we're talking about the performance of our system, we need to consider the whole system. We can't just talk about the JVM. We've spent all of our time talking about the compiler, but of course we'd have to worry about the GC too. And our JVM is running on top of an operating system. And a lot of us are now using virtualization, so it's not just an operating system. We're also virtualized for running on something like AWS or VMware. And then there's the hardware. And even the hardware is not that simple. To put it in the terms of Martin Thompson, who writes a lot about low latency Java, we need to have mechanical sympathy, which is actually a term he borrowed from race car drivers. We don't have to know everything about how our system works, but we need to know enough to understand our system's strengths and weaknesses. And just like the VM has weaknesses, our hardware does too. As we've seen before, our hardware is superscalar, meaning it can execute multiple things at the same time. And it has out-of-order execution, which makes writing concurrent programs really difficult. But even more than that, just like the JVM, it's sitting there profiling our program. And it figures out that a branch is always taken, or not taken, or taken on even iterations of the loop, but not odd iterations of the loop. And it can do this for direct branches and indirect branches, for virtual calls. And it can do this at a global level, or at a local level for a single loop. And it has multiple levels of caches, as we've already seen. And all of this has actually been true for 20 years. It started with the Pentium Pro in 1995. In fact, your modern Intel isn't even really a CISC processor. It's actually a CISC facade on top of a RISC core. The CISC instructions are broken down into micro-ops. And that all started with the Pentium Pro as well. And this level of indirection leads to some surprises. For instance, let's compare the performance of an array list and a linked list using a JMH benchmark, the list face-off. The JMH benchmark has a linked list and an array list, and it parameterizes them using the sizes for all the powers of 2 from 1 to 1,048,576. All the test data is set up in a single setup method, and then there's a benchmark that iterates over the linked list and over the array list, just computing the OR of the hash codes of all the strings that make up the list. And that's it. And we think these are both order in. They should both take the same amount of time, but they don't. Let's run the benchmark and see. And here are the results. And hopefully now you can see why I chose powers of 2 for size. It makes it easy to go down the table and see if the numbers really are doubling as we expect. And by and large, for array lists, they appear to be. And for linked list, the story is similar, albeit with some variation. But do you notice the linked list numbers seem a bit higher? For instance, 512 items for ArrayList only took 975 nanoseconds, but for linked list it took 2400 nanoseconds. And this trend continues. All the way up to 1,000,000, linked list is taking 50% longer. Is that really the case? Well, let's plot it and see what we see. Here we have the results plotted on a graph. And we can see that linked list, while it appears to be order in, it is linear. It is always slower than the array list. And this is of course because their constant factor is different. But why would that be? Well, remember, memory is complicated. On a modern system, we have an L1 cache, an L2 cache, a shared L3 cache, and main memory. And it takes increasingly more cycles and time to go through these different levels. And the more memory something takes up, the more we're going to have to do this. The linked list looks like this in memory. There's our string object, which would also have a string array, and it's pointed to by a node, the dark blue. And every node has a pointer to the next node. And so every element we put in our list actually requires allocating an object. And of course, this makes the whole thing take up more memory. More memory means more work loading things and getting it to the processor. It would also mean more work for the garbage collector. Every object has a header, and so all these objects have extra bytes just for metadata. And that all has to be copied by the garbage collector and loaded into memory, and that's a lot more work. Let's compare how the array list would be laid out in memory. It's a lot simpler because, well, it uses an array. And an array in Java is a contiguous piece of memory. So the dark blue, our spine, is all just in one location. And then the objects may be scattered around. This takes up a lot less space. It's a lot less work to load things into memory. But there are other nice properties that come from this as well. Because the array is itself a contiguous piece of memory, when we load the first element into cache, we don't load just the first element, we'll load 8 or 16. because they're all in the same cache line. And even better for a large array, the hardware will figure out what we're doing. As we go through the array, it'll realize you're accessing memory address plus 0, and then memory address plus 8, and then 16, and 24. It'll say, ah, I see what's happening here. And it'll go ahead and start to load the next piece of memory in advance and pull it into the L3 cache so that we never have to go out to main memory. And the array list will perform much better. Now this all depends on how everything gets laid out in memory, and different garbage collectors will affect that. So again, you have to look at the system as a whole. But a lot of the things that you thought were true, that a linked list should be just as good as an array list, they're not true anymore. A linked list is great if you only need to insert from the head or the tail, or if you need something that you can do concurrently, then you could use a concurrent linked queue. But for a bulk read, an array list is clearly the winner. And the surprises that come from our memory subsystem don't just stop there. There's something called false sharing. Remember I just told you we load cache lines? Well, we also store cache lines. That's actually the unit of currency for reading or writing from main memory. And this has some very interesting implications. For instance, consider that I have an array of size 16 composed of longs. And I never have the same thread update the same counter at the same time. But sometimes two threads update those that are side by side. Or sometimes it updates the first one and the one 8 slots over in another cache line. Would this really make a difference? As it turns out, it does. Again, I'll use JMH to demonstrate, this time using the false sharing benchmark. What we're going to do is modify the elements of an atomic long array. But because our operations are going to be so fast, we're going to increase the number of forks, warm-up iterations, and measurement iterations to make sure that this result is real. And we're going to use two threads. One to modify the first element, another one to either modify the second or the 8th element. We're going to parameterize the test on what the other index is, 1 or 8, and somehow we have to have two threads updating different things. To do that, I'm going to use this thread data class, which has a state annotation with scope thread. So each thread will get its own instance. And I use an atomic integer to create a counter so I know the thread ID. The first thread is going to update the first element, and the second thread is going to update the other index. And then JMH will pass our thread data to our benchmark method. If our benchmark method has a thread ID of 0, we update element 0. Otherwise, we update the other index. Let's run this benchmark and see what it does. Once again, because I bumped up the number of warm-up iterations and iterations, this is going to take a little bit to run. And here are the results. For an other index of 1, that is, in the same cache line of index 0, 64 nanoseconds per increment, versus the index of 8, 41 nanoseconds per increment. Admittedly, with more variation than I would like. But this is a repeatable result. Because element 8 is in its own cache line, it doesn't fight with element 0 for the cache line. And this does make a difference, believe it or not. This is a micro-optimization that matters, and it's actually one that the JDK authors have worried about. If you open up your JDK and you go search in SunMISC, you'll find a new annotation in Java 8, contended. And because it's in SunMISC, you won't necessarily find out a lot about what it's for. But what it's for is to say that this is a field that's updated a lot. And because it's updated a lot, it might adversely affect things around it. We might run into this false sharing problem. And one way to solve it, give that field its own cache line. And that's what @contended does. As hopefully you can see from our brief look into the hardware, as you dig deeper, it only gets more surprising about what's worth optimizing and what isn't. So my last word of caution before we conclude the series, what's worth optimizing? Throughout the series, we've looked at some of the optimizations that HotSpot can perform, and last time we even looked at some of the optimizations that the hardware can perform. But this still raises the question, where should we spend our time optimizing? And the answer often isn't Java. We could have I/O issues on our network. We could have inefficient SQL queries, and we should really be looking at our SQL query plans. We could have missing caching that we should add. And sometimes maybe we'll have something algorithmic. But Java? Honestly, HotSpot usually does a pretty good job. So how do we know if it didn't? Well, You've probably heard at least part of this quote about premature optimization being the root of all evil. But there's a little more context to the quote that's often left out. What Knuth actually said is we should forget about small efficiencies, say about 97% of the time. Premature optimization is the root of all evil, yet we should not pass up our opportunities in that critical 3%. And it really is something like 3%. A very small portion of our code is really hot. Spending our time optimizing anywhere else doesn't accomplish a whole lot. If you get a 90% efficiency improvement in a piece of code that's only used 1% of the time, that's still a 0.9% gain. That's probably not really worth it. And while it's true that we only spend a small amount of our time in most of our program, I think we often misuse this quote to justify not doing certain things too. It's not premature optimization to pick the right type of collection. That is, to pick a hash map whenever it's appropriate, or an array list where it's appropriate. So it's not wrong to pick an array list instead of a linked list, or to pick a concurrent collection where you need to reduce contention. But it might be wrong to add a cache or some types of index prematurely. Those things have setup cost, and if they're not working, they're not worth having. Oftentimes we try to add cache as a band-aid, but then we don't actually even bother to check what the hit ratio of our cache is. If the hit ratio of our cache is low, it's just unnecessary complication. So we have to be really careful about what we mean by premature optimization. It can be good, it can be bad, but you have to be smart about it. But if you're just not sure, you have to use some sort of tool to find what piece of code is hot, to find where you need to spend your time and effort optimizing. And for that, we're going to use some profilers. In Java, there are many profilers available, both commercial and free, and they use both sampling and instrumentation to gather their data. I'm going to show you several of the free ones that come with HotSpot and explain to you the strengths and weaknesses of those profilers. But first, we're going to need something to profile. And for that, I have a very simple Jetty server that simply serves the string hello world. The actual message contents are created in the static initializer block. So there's not much work actually happening when we hit the server. And here's the main. It simply sets up a server on 8080 with a new default handler and responds with our hello world bytes that we set up before. That's it. To make it easy for you to run yourself, I've included a Jetty project directory, which includes a Maven build. And if you run mvn install, it will actually create an executable jar. Switching to the target directory, now we can run our jar file. And now we should have a running server. We'll verify that by using a browser and going to localhost 8080. And there we go. Hello world. Now we have something to profile. We'll start our profiling of Jetty with the oldest profiler included with the JDK, hprof. To do that, we'll rerun Jetty, but this time with some extra arguments. We'll add agentlib, hprof, and we're going to do CPU sampling, which we specify with equals CPU equals samples, and then we run Jetty again. And right now I'm just going to run it under no load whatsoever, just so we can establish a baseline and see what our profile looks like. Now it's been running for a few seconds, I'm going to kill it, and hprof will dump a file showing us the usage. You'll find that in our directory from which you ran Jetty. It's called java.hprof. The file starts with some legalese, but if you scroll down, you'll see some thread samples, and at the bottom we can actually see a summary. We spent 66% of our time in KQ array wrapper kEvent0, and 33% of our time in server socket channel impl except 0. If you weren't already aware, methods ending with 0 tend to be native methods in the JDK. So these are both native methods interacting with the I/O layer. Since I'm using macOS, it's using kEvents as its underlying mechanism, and except is simply waiting for connections. And this makes sense. Our server wasn't actually serving any traffic, so it was basically just spending all its time waiting. And I guess that's a useful result, but how helpful is it really to know where our application was not spending its time? I guess it would tell us we have too many threads doing nothing, but what if I had threads doing something? They might just get lost in the noise. Well, let's try putting the server under some load to find out. So I'm going to run Jetty again, exactly as before, using hprof with CPU samples. But this time I'm going to generate some load using jmeter. Now typically you shouldn't generate the load from the same machine that's actually running your server, But for our purposes, this is good enough. And you can pick any load generation tool you like. I'm just choosing JMeter because it's one a lot of people are familiar with. So we'll start running. We'll let it run for a little bit, and then we'll see if our report's any different. We can already see there are a lot more traces, a lot more threads were actually doing something, and our activity looks a bit different. But KQ array wrapper and server socket channel impl are still on top, because hprof is sampling all the threads, not just the threads that are actually doing something. And most of the threads, they're still not doing anything, so they're still just sleeping, at least most of the time. Yes, we can now see that the file dispatcher impl write v is now closer to the top, but it's a lot of work to dig through this, because we're showing a bunch of stuff that's just not relevant. But there's something even more insidious happening here. Consider you had three functions, a, b, and c. A calls b calls c. Is it possible that despite the fact that c takes up 50% of the time, you would never see a sample in c? Say, well, in the short run, yes, but in the long run, of course not. Alas, that's not true. All of the profilers that use sampling, until very recently, they sit on top of JVM-TI, the Java VM's tool interface. And that sampling mechanism is shared by all of them, and it only samples at safe points. These are garbage collectible points, and not every method has one. If a function has a large computational loop, just using numbers, not really using objects, or it's doing a large array copy, it may not have a safe point, and it will never show up. So there are only certain sites that are actually sample eligible, and so the sampling can be skewed. Now hopefully you'll know this, and you'll see that B is near the top of the list, and from that you'll be able to deduce that, okay, C might still be an issue. But it is possible to be misled, and so you should at least be aware of it. But of course there is another option. We don't just have to use sampling. The profilers also support instrumentation. So next time, we'll look at that. Last time, we started to investigate where the hot points are in our Java programs by using profilers. And we saw some of the downsides of sample-based profiling. This time, we're going to look at the alternative, instrumentation-based profiling. And of course, we'll need something to measure. This time, we're going to return to our simple program from much earlier. As you recall, this program allocates 1,000 objects at a time in an inner loop and measures the performance with an outer loop. But because of dead code elimination, inner loop runs impossibly fast. It runs in no type at all because the VM just doesn't actually have to allocate any objects. Let's see if our profiler agrees. Again, we'll run with hprof at command line, but let's first run the program just as is to remind ourselves of the baseline performance. I'm using Java 8, and as you can see, the last few iterations take mere tens of nanoseconds to allocate 1,000 objects, because they're not really allocating. Now let's try it with hprof. Again, we'll use the agent lib, hprof, but this time with heap equals sites, which finds allocation sites, and I'm also going to run with print compilation. Can you see how much higher the iteration values are? Rather than taking tens of nanoseconds, it's now taking 5, 6, 7 million nanoseconds for 1,000 objects. This is the overhead of hprof. But, okay, so that's the downside of using hprof. They at least give us accurate results. And if we scroll to the bottom, we can see, well, hprof says we allocated 300,000 objects, which is indeed what we would expect. 1,000 iterations of the inner loop times 300 iterations of the outer loop, that's 300,000 objects. But we already know this doesn't actually allocate those objects. So what's going on here? That can't possibly be right, and it's not. If we search our output for object init, we can see object init is now 5 bytes. But the object constructor is empty. It should be a single byte, just a return. So what's happened? hprof has rewritten object init to contain tracking code to tracker object init, which you can see in the line below. And by doing that, it's actually made it hard for the just-in-time compiler to realize that the object is dead. And it actually causes the object to be alive, and causes the performance to become bad. And so hprof has accurately indicated that we could allocate 300,000 objects at that allocation site, but in doing so, it's actually made it so, and completely skewed the result. Now at this point, I should tell you, you really shouldn't use hprof. HProf was actually intended more as a tech demo to show what was possible for vendors to do with the JVM tools interface. There's actually now a JEP to remove it because there's something better. One of those is Visual VM. So let's try the same test, but now with Visual VM. If you have a late JDK 6, you should already have Visual VM. All you have to do is type jvisualvm at command line and a GUI will appear. And the way Visual VM works, when I start applications, they will appear in the left pane. So rather than having a short running application, I'm going to modify our program to run a little bit longer. What we're actually going to use is the revisiting simple program example, where I've actually removed the terminal condition for the outer loop entirely, but I've also changed it so that the output only occurs every 100,000th iteration of the outer loop, because this program is going to run a while and I don't want it to overwhelm the machine. These changes, while small, do actually change the performance of the program, so we're going to run it again just to establish a new baseline. And we can see each group is taking about a few hundred nanoseconds now, rather than just 60-70 nanoseconds. But that's okay, we know what to expect. Now we'll go to Visual VM, and we'll find our sample program in the left panel, and open it. As with HProf, we could either sample, or we could use the profiler. The profiler performs instrumentation. So when I click the memory button, we'll see the GUI indicate that it's instrumenting classes. And if we go over to the terminal, we can see the instrumentation happening as well. Let's see if this has affected our output. It has. Our numbers have jumped to about 40,000 nanoseconds. But this is a lot less of an impact than HProf had. And it turns out Visual VM is actually a much more accurate tool for this type of profiling. If we look at the actual results, we can see that Visual VM is correctly telling us that objects are not being allocated excessively. Whereas HProf, it told us hundreds of thousands of objects were being allocated, even though that simply wasn't the case. But despite this, there's still a problem with Visual VM. It's still instrumenting classes, and that's a problem, because that's changing the bytecode. That's changing the very thing we're trying to measure. And if we were trying to measure CPU in some way, this could have a big impact. Remember that inlining is one of the most, if not the most important optimization the compiler does. And inlining in HotSpot is largely driven by bytecode size. So even small additions to the bytecode to just log the entry and exit of a method could have a profound impact on the decisions the compiler makes. And then you're not really measuring what you think you're measuring. And that's not to say instrumentation is bad or sampling is bad. You just have to understand the effects they may have. They may well get you in the ballpark, but understand you may still be off by a bit, or in the case of the HProf example, off by a mile. Fortunately, others have come before us, and they've realized the problems with our profilers, and they've created more honest profiling tools. In fact, one of them is actually included with the latest JDKs, Java Mission Control, and that's what we'll talk about next time. In the prior two segments, we saw how profilers can be dishonest, either through sampling that only happens at safe points and may miss crucial functions entirely, or through instrumentation that, while providing an honest depiction of code, provides an honest depiction of code that's been modified. And so, what it's providing a picture of may be not what we were doing at all, because it can destroy core optimizations like inlining and other things that are sensitive to code size. So this time we're going to talk about more honest profilers, those that can sample at non-safe points and don't rely on invasive instrumentation. One of the earliest of these was the Google Lightweight Java Profiler, which was created for internal use at Google. It is available on GitHub, but it requires a fair amount of work to set up, so I wouldn't necessarily recommend it. Instead, if you're looking for a free honest profiler, I'd recommend The Honest Profiler by Richard Warburton, which also includes a nice GUI. It does take a fair amount of work to build and set up, but it is free to use in any environment. Unlike the one I'm actually going to demonstrate, Mission Control. Mission Control is included with late versions of Java 7, but it is not free to use in production. You have to pay Oracle an additional fee to use it in production. However, you can use it in your development environments. But be sure to read the details before you start using Mission Control to make sure you're not in violations of the license terms. To demonstrate Mission Control, I'm going to again use our simple Jetty server from before, along with JMeter to create load. Just to remind you, our server is quite simple. It simply responds to all requests with a static response of hello world. I'm going to switch to command line to launch Jetty, But I need to tell you a few things about the version of Java I'm using first. I'm using Java 18066. Early versions of Java 8 will not work. They lack the supported features. And unfortunately, versions of Java before Java 8 will also not work. And OpenJDK builds will not work either. You need a final release build from Oracle. Only the Oracle builds of HotSpot include the features necessary for mission control. They are not part of OpenJDK. Now that you know the details about the version of Java you need, we're going to launch it. And we're going to use a rather lengthy set of command line flags. XX:+ unlock commercial features. This is the flag that says that you're either not running this in production or you've paid the appropriate fee to Oracle. XX:+ flight recorder, which is the flag that specifies to turn on the capability to do detailed tracing that's needed by mission control. XX:+ unlock diagnostic VM options, which we've used before, and XX:+ debug non-safe points, which is the flag that allows us to trace at non-safe points, and is only available in late versions of Java 8. And then, of course, -jar and our jar file. And I'm going to run it in the background. And I'm going to launch mission control, which I just do by typing JMC since it is on my path. With mission control launched, I can now see in the left panel, the JVM browser, my Jetty jar. And if I click on it, I can see flight recorder, and I could start flight recording. Right now, Jetty's not under load, so I'm going to call this Jetty no load. And the recording process takes, well, in this case, 60 seconds because that's the default recording time. But you can change it to be longer or shorter as you desire. With the trace complete, mission control now shows a GUI of the results. To see what code was hot, I can switch to code in the left panel, and I can switch to hot methods in the lower set of tabs. And we can see, well, no methods were really hot. Just object stream class invoke read at one sample and timer thread main loop at another sample. And this is what we'd expect for a system that's not doing anything, after all. Jetty's not under any load. But this is a very different result than what we would see with HProf, or any of the other JVMTI, that is, the Java Virtual Machine Tool Interface-based profilers. But of course, this isn't very interesting. Let's put Jetty under some load and see if we actually get some more sensible results. Now going over to JMeter, using the same test we used before, I'm going to put the server under load. Now we should be doing requests to Jetty. Let's switch back to mission control and trace again. Now that the trace is complete, again, we'll switch to code and then to hot methods. And we can see that we now have a lot more hot methods. And the ones that are at the top seem to be array try, which is probably for bytes in the request, an abstract string builder for building the response, and HTTP parser for parsing the headers. And that's exactly where we'd expect a loaded server to spend its time. This is a much useful trace than what you would get out of HProf. If you looked at something like HProf, the top two methods would be the same, regardless of whether the server was loaded or unloaded, and that's not very helpful. This gives you a much better idea of where your time is really going. Now, I think Mission Control is a great tool, but it is worth keeping the others in mind in case you either cannot pay for Mission Control, or you need to have the same capabilities, but you're running an older version of Java, or you're running OpenJDK. Mission Control is certainly the easiest to set up and probably has the prettiest GUI if it's an option for you, but the others are definitely worth considering as well. And with that, we've nearly reached the conclusion of our series, so next time we'll recap what we've covered. So we've reached the end of our series on Java performance. Throughout the series, we haven't just talked about little performance tweaks here and there. Instead, we talked about how HotSpot works and how that influences the performance of our applications. The importance of the profiling in the interpreter to feed into the just-in-time compiler to do profile-driven optimizations, including speculative optimizations, which are enabled through de-optimization. And we talked about tools to see that all these things are happening. Jitwatch to see the bytecode and even the machine code and what methods were just-in-time compiled. Java measurement harness to remove the uncertainty from our measurements to make sure that our applications are warmed up and we're really measuring the right phase of execution. And mission control to make sure we're getting an honest view of where our time is going, rather than some of the other profilers, which can provide skewed profiles in a number of different ways. And we've learned the importance of the different types of optimizations, the role of intrinsic methods, the role of static optimizations, both local and global, the importance of interprocedural optimizations, and speculative optimizations. And we've learned that while these optimizations are seemingly obvious and a good idea, they can have some very surprising implications in certain contexts. Particularly when we start trying to write concurrent code, these optimizations that worked to our advantage before can quickly prove harmful. And we've seen that while speculative optimization is a powerful tool that we need to make Java code run quickly, it does come with the cost of de-optimization, which will send us back to the interpreter, which is orders of magnitude slower than C2, the server compiler. And most importantly, we've learned how all these things fit together. No optimization by itself is really all that important. It's how they add up and how they interact that allows our programs to run much faster than they would otherwise. And if you know how it works, then you can let HotSpot do a lot of the work for you. You just need to learn a few simple things so that you don't trip it up. And then it can do all of the rest for you, and you avoid unnecessary work while still getting things to run fast. But with all that said, you also need to keep in mind, optimization is an ongoing problem. HotSpot keeps improving. Optimizations that are beneficial today may become unnecessary, or worse, they could even become harmful. And so you have to profile and benchmark carefully and really continuously, because what worked today may not hold up the next day. And if you really want to get the most out of applications, you need to understand all the layers of your system. You can't just stop with HotSpot. It's an excellent start, but you also need to learn about your operating system and especially your hardware. Your hardware is a very complicated beast unto itself, and to really understand what's going on, you have to go a little deeper. And with that, we've reached the end of our series. I thank you all very much for listening.